Have you ever gazed at the night sky and wondered what secrets lie hidden in the vastness above us? Despite the incredible progress science has made, there are still mysteries in the universe that baffle even the brightest minds. Questions about how it all began, what keeps it going, and what might come next continue to challenge our understanding. The universe is a place of extremes, from massive stars that dwarf our sun to particles so tiny they're almost unimaginable. Yet, for all our progress in exploring these extremes, there are still gaps in what we know. These gaps aren't just small holes in our knowledge, they're vast chasms. For example, do we really understand how the universe started? What existed before the Big Bang? Scientists have theories, but these theories only push the mystery further back. Then there are the phenomena we see but can't explain, like fast bursts of energy or objects in space that behave in unexpected ways. How do we even begin to unravel these puzzles? Is it enough to rely on telescopes and equations? Or is there something we're missing in the way we approach these questions? The answers may be out there, but finding them requires us to ask the right questions. Let's start with one of the biggest questions: where did it all begin? If the universe started with the Big Bang, what caused it? The theory tells us the universe was once incredibly small, hot, and dense. But why did it explode into what we see today? Was there a spark? Was it inevitable? Some scientists suggest there was nothing before the Big Bang. But can nothing really exist? Others propose that the universe could be part of an endless cycle of expansions and contractions, like a cosmic heartbeat. If that's true, how many times has this happened? Could it happen again? Another mystery ties directly to our attempts to understand the universe's early moments: the concept of inflation. Inflation suggests that the universe expanded faster than the speed of light for a fraction of a second after the Big Bang. But what triggered this rapid expansion? Why did it stop? And perhaps most intriguingly, is there evidence of other inflated regions beyond what we can see? The universe we observe today is only a fraction of the full picture. Telescopes give us glimpses of the distant past, but the earliest times remain hidden. There is a period called the Dark Ages of the universe, when the first stars hadn't yet formed and there was no visible light. How do we study a time when light itself didn't exist? We rely on indirect evidence, like cosmic microwave background radiation. This faint glow comes from the early universe and contains clues about its first moments, but even this radiation has anomalies, patterns we can't fully explain. Are these patterns random, or do they point to something deeper? Every time we answer one question, it seems like two more take its place. For instance, the idea that the universe is expanding faster than expected led to the discovery of dark energy. Dark energy is thought to make up most of the universe, but we don't know what it is. It's a term we use to describe something unknown. What could dark energy really be? The mysteries don't stop with the large-scale structure of the universe. Even the smallest particles challenge us. At the quantum level, particles behave in ways that defy common sense. How does this connect to the larger universe? Does the strange behavior of quantum particles hold the key to understanding the cosmos? Or is it just another layer of complexity? As we explore these questions, one thing becomes clear: the universe is both stranger and more wonderful than we ever imagined. It's not just a collection of stars, planets, and galaxies. It's a place of constant motion and change, where forces we don't fully understand shape everything we see and much we can't. But understanding the universe isn't just about looking outward, it's also about looking inward. How do we fit into this vast puzzle? Are we just observers, or do we play some role in the universe's story? Could the act of observing the universe change what we see? These questions aren't just for scientists, they're for anyone who's ever wondered why we're here, how it all began, and what might come next. The mysteries of the universe belong to all of us. And each mystery is an invitation to learn more. In this video, we'll explore some of the greatest unanswered questions about the universe. These are the puzzles that keep scientists awake at night. Some are new, emerging from the latest discoveries. Others have been around for decades, resisting every attempt to solve them. So, as we dive into these mysteries, let's keep asking questions, because in the end, every question brings us closer to understanding the universe and our place within it. Where did everything come from? This is one of the biggest questions humans have ever asked. The universe, with its galaxies, stars, and planets, had a beginning. But what happened before that beginning, scientists call this the Big Bang. But even the term Big Bang doesn't fully explain what happened. The Big Bang wasn't an explosion in space. It was the rapid expansion of space itself. At some point, about 13.8 billion years ago, everything we see today was packed into a space smaller than an atom. Then, in a fraction of a second, it started expanding. But why did it expand? What caused this moment? Some theories suggest that before the Big Bang, there was nothing. But this idea is hard to understand. What does nothing really mean? If there was nothing, where did the energy and matter for the universe come from? Did the universe come from something we can't yet detect? Others suggest that the Big Bang wasn't the true beginning. Instead, it might have been one event in an endless cycle. According to this idea, the universe expands, collapses, and then starts again. This means there could have been countless universes before ours. If that's true, how many cycles have there been? One of the biggest puzzles about the Big Bang is what happened in the first few moments. In those moments, the universe grew incredibly fast, faster than the speed of light. Scientists call this inflation. But why did inflation happen? What caused the universe to expand so quickly? And why did it stop? To make things even stranger, we can only see part of the universe. The part we can observe is limited by the speed of light. Light takes time to travel, so when we look far away, we're seeing the past. But there's a limit to how far we can see. This means there could be regions of the universe beyond what we can observe, regions that might never be visible to us. Could there be other universes beyond our own? Inflation theory suggests this might be possible. If inflation created our universe, it might have also created others. These other universes could have different physical laws and constants. Some might have no stars or galaxies. Others might be completely empty. But how do we prove this? If we can't see these other universes, how do we know they exist? Scientists look for indirect evidence. They study patterns in the cosmic microwave background, a faint glow left over from the early universe. This glow contains information about the universe's first moments. The cosmic microwave background isn't smooth. It has tiny variations in temperature. These variations tell us about the early structure of the universe. But some patterns don't match what we expect. Could these strange patterns be evidence of another universe interacting with ours? Or are they simply random? Another puzzle is the time before stars formed. This period is called the Cosmic Dark Ages. During this time, the universe was filled with gas, but no light. Without light, it's almost impossible to observe what happened. How did the first stars form in this dark era? The first stars were very different from the stars we see today. They were massive and burned through their fuel quickly. These stars created the first heavy elements, which were necessary for planets and life to form. But where did these first stars come from? It's hard to imagine a time without galaxies, stars, or planets. But this is how the universe began. The gas in the early universe was almost uniform, with only tiny differences in density. Over time, gravity pulled the denser regions together, forming the first structures. But why were there differences in density in the first place? Even the gas itself is a mystery. The early universe was mostly hydrogen and helium. Where did these elements come from? Scientists believe they were created in the first few minutes after the Big Bang. But why only these elements? And why in these specific amounts? As the universe expanded, it cooled. This cooling allowed atoms to form. Atoms are the building blocks of matter. Without them, there would be no stars, no planets, and no life. But why did the universe cool in just the right way to allow atoms to form? Every discovery about the universe's origins leads to more questions. For example, why does the universe look the same in all directions? This uniformity is surprising. It suggests that different regions of the universe were once in contact, but if these regions were moving away from each other at faster than light speeds during inflation, how could they have communicated? This puzzle is known as the horizon problem. Scientists try to solve it with inflation theory. They suggest that before inflation, the universe was small enough for all regions to interact. But this explanation raises another question: what caused inflation to begin? Some scientists propose that inflation was caused by a special type of energy. This energy, called the inflation field, is hypothetical. We've never observed it directly. If it exists, where did it come from? Did it have a beginning, or has it always been there? Even the shape of the universe is a mystery. Is it infinite, or does it have an edge? If it's infinite, how did it become that way? If it has an edge, what lies beyond it? Current observations suggest the universe is flat on large scales, but what does flat mean in this context? The more we learn about the universe's origins, the more complicated the picture becomes. Each question leads to more questions. For instance, what role did dark matter play in the early universe? Dark matter doesn't emit light, so we can't see it, but its gravity affects the motion of galaxies. Did dark matter help form the first structures in the universe? And what about dark energy? If dark energy is causing the universe to expand faster today, did it play a role in inflation? Are dark energy and the inflation field connected, or are they completely separate phenomena? The origins of the universe are a puzzle with many pieces. Some pieces fit together, but others don't. Scientists use models and simulations to test their ideas. They try to recreate the conditions of the early universe, but these models are limited by our current knowledge. We've come a long way in understanding the universe's beginnings, but there's still so much we don't know. What triggered the Big Bang? What came before it? What role did dark matter and dark energy play? These are questions we continue to explore. The story of the universe's origins is far from complete. It's a story of questions, puzzles, and mysteries. And as we seek answers, we uncover even more fascinating questions about the cosmos. Have you ever thought about what holds galaxies together? Stars and galaxies move at incredible speeds. Based on their mass, they should fly apart, but they don't. Why something invisible is keeping them together? Scientists call it dark matter. Dark matter doesn't emit light. It doesn't reflect light, and it doesn't absorb light. This means we can't see it, but its presence can be detected because of its gravitational effects. For example, when scientists measure the speed of stars orbiting in galaxies, the speeds don't match the amount of visible mass. There must be extra, unseen mass. What is dark matter made of? Scientists aren't sure. It might be a type of particle we haven't discovered yet. Some think it could be weakly interacting massive particles, or WIMPs. Others suggest actions, which are extremely light particles. Both are just theories. Though, because no one has directly observed these particles, dark matter forms halos around galaxies. These halos are regions where dark matter is more concentrated. They affect how galaxies form and evolve. Without dark matter, galaxies might never have formed. But why does dark matter gather in halos? And why doesn't it form stars or planets like regular matter? If dark matter is invisible, how do scientists study it? They use methods like gravitational lensing. This happens when a massive object bends light from a distant source. By studying the light's distortion, scientists can estimate the mass of the object. Sometimes, the mass calculated is much larger than the visible matter. This extra mass is attributed to dark matter. Another method is studying the cosmic microwave background. This radiation shows patterns in the early universe. These patterns reveal how matter was distributed. The data suggests that most of the matter in the universe is dark matter. But why is there so much more dark matter than normal matter? What about dark energy? While dark matter holds things together, dark energy does the opposite. It pushes the universe apart. Scientists discovered that the universe is expanding faster over time. This was unexpected. They thought gravity would slow the expansion. Instead, it's speeding up. Dark energy is thought to be responsible for this acceleration. But what is it? Like dark matter, dark energy is not directly observable. It's a name given to explain the unknown force causing this phenomenon. Is it a property of space itself? Some scientists think so. Others believe it could be a new field or particle. Dark energy makes up about 68% of the universe, while dark matter makes up about 27%. That means visible matter, everything we can see, is only about 5% of the universe. Why is the universe made up this way? Could there be more forms of matter or energy we haven't discovered yet? One idea is that dark energy might be related to the vacuum of space. Even empty space isn't truly empty. It has energy. This is called vacuum energy. Could dark energy be linked to this vacuum energy? If so, why is its effect so strong over large distances but weak on small scales? Dark energy also creates questions about the universe's fate. If it continues pushing galaxies apart, will it eventually tear them apart? Some theories suggest this could happen in a scenario called the Big Rip. In this scenario, the expansion becomes so fast that even atoms are pulled apart. Could dark matter and dark energy be connected? Some theories suggest they might come from the same fundamental force or particle. If true, understanding one might help us understand the other. But so far, no evidence links them directly. There are also alternative ideas. Some scientists think dark matter and dark energy don't exist. Instead, they propose modifying the laws of gravity. These modified theories aim to explain the same phenomena without introducing new substances. But these ideas have their own challenges. One mystery about dark matter is why it doesn't interact with regular matter. Normal matter interacts through forces like electromagnetism. This allows us to see and touch it. Dark matter seems to interact only through gravity. Why doesn't it interact in other ways? Some experiments are designed to detect dark matter particles. Scientists build underground detectors to shield them from other particles. These detectors are extremely sensitive, yet so far, no dark matter particle has been found. Why is it so hard to detect? Another method is searching for dark matter in space. Colliding galaxies and other cosmic events may reveal clues. For example, the Bullet Cluster is a pair of colliding galaxy clusters. Observations suggest that dark matter separated from the visible matter during the collision. How does this separation occur? While dark matter holds galaxies together, it also creates questions about how galaxies behave. For example, simulations show that galaxies with dark matter should have specific shapes. Yet some observed galaxies don't match these shapes. Why do these differences exist? On the largest scales, dark energy shapes the universe. Observations show that galaxies are moving away from each other at increasing speeds. This means space itself is stretching, what causes space to stretch. Dark energy might also affect the universe's geometry. Measurements suggest the universe is flat on large scales. This flatness might be linked to dark energy, but why would dark energy cause a flat universe? Another puzzle is how dark energy has changed over time. In the early universe, dark energy had little effect, gravity dominated, and galaxies formed. As the universe expanded, dark energy became more influential. Why did this shift happen? Some scientists propose that dark energy isn't constant. Instead, it might vary over time, if it changes. What causes it to change? Could future observations reveal a pattern in how dark energy evolves? The study of dark matter and dark energy relies on technology. New telescopes and instruments are designed to gather more data. For example, the Vera-C Rubin Observatory aims to map dark matter in galaxies. Will it provide new insights? The mysteries of dark matter and dark energy remain unsolved. They challenge our understanding of physics and the universe itself. Could solving these puzzles reveal even deeper questions? Only time and continued exploration will tell. What happens when a star dies? If it's massive enough, it can collapse into something so dense that not even light can escape. This is what we call a black hole. Black holes are one of the most mysterious objects in the universe. But how much do we really know about them? Black holes are formed when gravity wins. In a massive star, the outward pressure from nuclear fusion balances the inward pull of gravity. But when the star runs out of fuel, this balance breaks. Gravity pulls the star inward until it collapses into a single point called a singularity. The singularity is a place where density becomes infinite. Time and space, as we understand them, no longer work there. But what does this mean? Does the singularity truly exist? Or is it a sign that our understanding of physics is incomplete? Surrounding the singularity is the event horizon. This is the boundary of the black hole. Once something crosses the event horizon, it cannot escape. Why? Because the escape velocity, how fast you'd need to travel to get away, is greater than the speed of light. But what happens at the event horizon to an outside observer? Anything falling into a black hole seems to slow down and freeze at the event horizon. The object's light becomes redder and dimmer until it disappears. Does this mean information about the object is lost? One of the biggest puzzles about black holes is the information paradox. According to quantum mechanics, information cannot be destroyed. But when something falls into a black hole, it seems to disappear forever. How can this be reconciled? Some scientists suggest that the information might be stored at the event horizon in a two-dimensional form, like a hologram. This idea is called the holographic principle. If true, it could change how we think about space and time. Black holes come in different sizes. There are stellar black holes, formed from collapsing stars. There are also supermassive black holes, which exist at the centers of galaxies. These can be millions or billions of times the mass of the Sun. But how do they form? Stellar black holes form from stars. But supermassive black holes are much larger. Did they grow by consuming stars and gas over billions of years? Or did they form differently? Perhaps from massive clouds of gas in the early universe. There's also a type of black hole called an intermediate mass black hole. These are smaller than supermassive black holes, but larger than stellar ones. They're harder to find and study. Why are they so rare? Another type of black hole is a primordial black hole. These could have formed shortly after the Big Bang from regions of dense matter. If they exist, they might provide clues about the early universe. But so far, no definitive evidence for primordial black holes has been found. Black holes don't just sit quietly in space. They interact with their surroundings. For example, when a black hole pulls in gas or stars, the material forms a disk around it. This is called an accretion disk. The material in the disk heats up and emits energy, often in the form of X-rays. But why does the material form a disk? Why doesn't it fall straight into the black hole? The answer lies in angular momentum. The gas and stars orbit the black hole, creating the disk. Over time, Friction and other forces cause the material to spiral inward. Sometimes, black holes shoot out jets of energy. These jets can stretch across vast distances, far beyond the size of the black hole itself. What causes these jets? How do black holes, which pull everything inward, also send energy outward? Another mystery involves black hole mergers. When two black holes collide, they form a single, larger black hole. This process releases energy in the form of gravitational waves. These waves ripple through spacetime and can be detected by instruments like LIGO and Virgo. But what happens inside the black hole after the merger? Gravitational waves have opened a new way to study black holes. Before, we could only observe them indirectly through their effects on nearby stars and gas. Now, we can listen to them through the waves they produce. What else might we learn from these waves? One of the strangest ideas about black holes is that they might connect to other regions of space and time. This idea is called a wormhole. A wormhole is a theoretical tunnel that could link distant parts of the universe. Could black holes be entrances to wormholes? Wormholes are purely theoretical. No evidence supports their existence, but they're interesting because they challenge our understanding of space and time. Could wormholes explain some of the strange properties of black holes? Then there's the question of what happens if you fall into a black hole. From the outside, you'd appear to slow down and freeze at the event horizon. But what would you experience? Would you be stretched and torn apart by the intense gravity, or would you reach the singularity? Some theories suggest that the singularity might not be the end. Instead, it could lead to another region of space-time. This idea is speculative, but it raises interesting questions. Could black holes be gateways to other universes? Black holes also challenge our understanding of time. Near a black hole, time slows down due to the intense gravity. This effect is called time dilation. But why does time behave this way? Black holes don't last forever. Over time, they lose mass through a process called Hawking radiation. This radiation occurs because of quantum effects near the event horizon. But how does this process work? Hawking radiation suggests that black holes can eventually evaporate completely. But if they disappear, what happens to the information they contained? Does it get released? Or is it gone forever? Studying black holes requires powerful tools. Telescopes like the Event Horizon Telescope capture images of black hole shadows. These images help scientists understand how black holes interact with light and matter. But how much can we learn from these images? Black holes are not just isolated objects, they influence their surroundings. For example, supermassive black holes at the centers of galaxies affect how those galaxies evolve. There are still many unanswered questions about black holes. Each discovery leads to more mysteries. What will we find as we continue exploring these strange objects? Only further research can reveal the answers. Is Earth the only place in the universe with life? This question has intrigued humans for centuries. To find an answer, scientists look beyond our solar system to planets orbiting other stars. These are called exoplanets. But how do we find them? Exoplanets are too far away to see directly with most telescopes. They don't emit their own light, and the light from their stars often hides them. So, scientists use indirect methods to detect them. One common method is the transit method. When an exoplanet passes in front of its star, it blocks a small amount of the star's light. This causes the star to appear dimmer for a short time. By observing these dips in brightness, scientists can determine the planet's size and orbit. But what if a planet doesn't pass in front of its star? How do we find those? Another method is the radial velocity technique. As a planet orbits its star, its gravity causes the star to wobble slightly. This wobble changes the light from the star in a measurable way. By studying these changes, scientists can detect the planet. Once an exoplanet is found, the next question is, Could it support life? Scientists focus on planets in the habitable zone, also called the Goldilocks zone. This is the region around a star where temperatures are just right for liquid water to exist. But is water the only requirement for life? Some exoplanets are rocky like Earth. Others are gas giants like Jupiter. Then there are super-Earths, which are larger than Earth but smaller than Neptune. Each type presents unique challenges and possibilities for hosting life. But which types are most likely to have the right conditions? Scientists also study a planet's atmosphere. The gases in an atmosphere can reveal a lot about the planet. For example, the presence of oxygen or methane might suggest biological activity. How do we study atmospheres from so far away? One method is spectroscopy. When light from a star passes through a planet's atmosphere, the atmosphere absorbs certain wavelengths. By studying this light, scientists can identify the gases present. But what if the signals are too faint to detect? Another challenge is distinguishing between natural processes and biological ones. For example, methane can be produced by both volcanoes and living organisms. How can we tell the difference? Not all exoplanets are in the habitable zone. Some are much closer to their stars and experience extreme heat. Others are far away and frozen. Could life exist in these harsh environments on Earth? Life exists in some of the most extreme places, from deep ocean vents to icy polar regions. This has led scientists to consider the possibility of life on exoplanets with extreme conditions. But would it be life as we know it, or something completely different? Some exoplanets orbit stars very different from our Sun. For example, red dwarf stars are smaller and cooler than the Sun. They are the most common type of star in the galaxy. Could planets around red dwarfs support life? Red dwarfs often have strong solar flares that could strip a planet's atmosphere. But some scientists think life could still exist underground or in oceans. How would we detect such life? There's also the question of time. Life on Earth took billions of years to evolve. If we find a planet with the right conditions, how likely is it that life has had enough time to develop there? The search for exoplanets raises another question. How many are there? Current estimates suggest there are billions of exoplanets in our galaxy alone. But how many are similar to Earth? The Kepler Space Telescope revolutionized our understanding of exoplanets. It discovered thousands of them, revealing that planets are common. Now, telescopes like the James Webb Space Telescope are taking the search further. What might they find? One of the most exciting discoveries would be a planet with biosignatures evidence of life. But what counts as a biosignature? Could we mistake something else for a sign of life? Even if we find a planet with signs of life, how would we communicate? The distances between stars are so vast that any message would take years or centuries to travel. Would we recognize a signal from another civilization? Some scientists focus on technosignatures, which are signs of advanced technology. These could include radio signals, artificial light, or other detectable markers. Have we already received such signals and not recognized them? The discovery of exoplanets also raises philosophical questions. If we find life elsewhere, what does that mean for humanity? Would it change how we see ourselves and our place in the universe? Exoplanets are incredibly diverse. Some are so close to their stars that their surfaces are molten. Others are tidally locked, meaning one side always faces the star while the other remains in darkness. How does this affect the possibility of life? Some exoplanets might have moons, similar to how Jupiter and Saturn have moons in our solar system. Could these moons be habitable? After all, in our own solar system, moons like Europa and Enceladus have subsurface oceans. The search for exoplanets is still in its early stages. We've only scratched the surface of what's out there. What surprises might the universe hold as we continue to explore? What is time? Is it a constant flow, or is it something more complex? From the moment we wake up to the second we fall asleep, time governs our lives, but how well do we understand it? Time feels straightforward. Seconds turn into minutes, minutes into hours. But when scientists study time, they discover that it's not so simple. Albert Einstein's theory of relativity showed that time can change. It can speed up or slow down depending on the situation. For example, time runs slower near a massive object like a star or a planet. This effect is called gravitational time dilation. Why does this happen? It's because gravity bends space and time. The stronger the gravity, the more time slows down. This has been tested with experiments. Scientists placed precise clocks on airplanes and compared them to clocks on the ground. The clocks on the airplanes ran slightly faster. How can something as steady as time behave this way? Then there's the question of the arrow of time. Time seems to flow in one direction, from the past to the future. But why the laws of physics don't require time to flow this way? Could time flow backward? In some situations, the arrow of time is often linked to entropy. Entropy measures disorder in a system. Over time, entropy increases. For example, a glass shatters into many pieces but never reassembles itself. Could entropy be the reason we experience time moving forward? Now, consider space. We think of space as a vast, empty area where objects exist. But space is not truly empty. It's filled with energy, and it can bend, stretch, and twist. How does this affect our understanding of the universe? Space and time are linked together. They form what scientists call spacetime. In spacetime, events happen in 4 dimensions, 3 for space and 1 for time. But why are space and time connected? Black holes offer a glimpse into the strange nature of spacetime. Near a black hole, space and time behave differently. Time slows down, and space is warped. Could this warping reveal deeper secrets about the structure of the universe? Another mystery is the concept of the multiverse. Some theories suggest that our universe is just one of many. If true, each universe could have its own version of space and time. Could there be universes where time flows differently, or doesn't exist at all? There's also the question of whether time has a beginning or an end. Did time start with the Big Bang? If so, what came before it? Some scientists believe time might not exist outside our universe. Others suggest time could be infinite. In physics, time is often treated as a dimension, similar to length, width, and height. But is time truly a dimension, or is it something else? Some theories suggest that time might emerge from deeper physical laws. What could those laws be? Quantum mechanics adds more puzzles to our understanding of time. In the quantum world, particles don't follow a simple timeline. They can exist in multiple states at once, and their behavior is unpredictable. How does this fit with the idea of time as a steady flow? One concept in quantum mechanics is superposition. A particle can be in multiple places at the same time until it's observed. Does this mean time itself is not fixed until we measure it? Another idea is that time might be an illusion. Some scientists propose that time is not fundamental. Instead, it could emerge from the way we perceive the universe. If true, what does this say about our understanding of reality? Time travel is another fascinating topic. The idea of moving through time has been explored in science fiction for decades. But could it be possible in real life? Einstein's equations allow for the possibility of time travel under certain conditions. For example, traveling close to the speed of light could cause time to slow down for the traveler. But could we travel backward in time? One theory involves wormholes. These are hypothetical tunnels in spacetime that could connect distant points. If wormholes exist, they might allow for time travel. But how could we create or stabilize a wormhole? Time loops are another possibility. These occur when events repeat themselves. In some theories, time loops could exist naturally in space-time. But if time loops are real, could they create paradoxes? Paradoxes are a major challenge for time travel. For example, the grandfather paradox asks what happens if you travel back in time and prevent your own existence. How could the timeline resolve such a contradiction? Even without time travel, time behaves strangely in different parts of the universe. Near a massive object, time slows down. In deep space, far from gravity, time speeds up. Could there be regions of the universe where time behaves in ways we can't imagine? Some scientists explore the possibility of timelessness. In this view, time doesn't flow. Instead, all moments exist simultaneously, like pages in a book. Could this explain some of the mysteries of time-space also holds its share of mysteries? For example, why is the universe so large? The observable universe spans billions of light years, yet it's just a fraction of the total universe. What lies beyond what we can see? The expansion of the universe raises another question. Space is stretching, causing galaxies to move apart. But what is space expanding into? Does it have a boundary, or is it infinite? Some theories suggest that space is curved. On small scales, space appears flat, but on larger scales, it might curve, similar to the surface of a sphere. Could the shape of space reveal hidden dimensions? There's also the mystery of quantum foam. On the smallest scales, space is not smooth. Instead, it's thought to be a chaotic, fluctuating foam. How does this quantum nature of space affect the larger universe? Scientists are also puzzled by the connection between space-time and gravity. Einstein showed that gravity is the bending of space-time. But why does space-time bend? What is the fundamental cause of gravity? Another question is whether space and time can be separated. In our everyday experience, they seem distinct. But in the universe, they're deeply connected. Could we ever study one without the other? As we explore space and time, we uncover more questions than answers. What secrets will the universe reveal as we continue to investigate its fundamental nature? Do we really think we're alone in the universe? It's one of the biggest questions humanity has ever faced. Despite all the stars, planets, and galaxies out there, we still haven't found any evidence of other life forms. Why is that? Could it be that we're not looking in the right way? Or is the answer much more complicated? In 1950, physicist Enrico Fermi asked a simple yet profound question: if the universe is so vast and old, with billions of stars and planets, why haven't we seen any aliens? This question is known as the Fermi paradox. The paradox becomes even more puzzling when we consider how old the universe is. There has been more than enough time for intelligent civilizations to develop, explore, and even colonize other star systems. Yet we haven't detected any clear signs of them. One possible explanation is that intelligent life is extremely rare. Maybe the conditions that allow life to emerge are so specific that they almost never happen. Another idea is that civilizations don't last long. They might destroy themselves with wars, resource depletion, or environmental collapse before they can explore the stars. But what if we are simply missing the evidence? Could alien civilizations be communicating in ways we don't understand? For instance, they might use technologies far beyond anything we can imagine. What if their messages are hidden in dimensions we can't access? In 2017, astronomers noticed a strange object passing through our solar system. They named it Oumuamua, which means scout in Hawaiian. This object didn't look or behave like anything we'd seen before. Most comets and asteroids follow predictable paths, but Oumuamua didn't. It had an unusual shape, like a long, thin cigar, and it moved in a way that didn't match the effects of gravity alone. Some scientists suggested it might be an alien probe sent to study our solar system. Of course, there are more natural explanations too. It could be a chunk of debris from another star system. But why was its shape so unusual? Why didn't it leave a trail like most comets? Could there be more interstellar visitors, like Oumuamua, that we've missed? We've found thousands of exoplanets, planets that orbit stars outside our solar system. Some of them are in what we call the habitable zone, where conditions might allow liquid water to exist. Water is crucial for life as we know it. So these planets are prime targets in the search for extraterrestrial life. Scientists look for biosignatures, signs that life might exist on these planets. This could include specific gases like oxygen or methane in the atmosphere, which are often produced by living organisms. But detecting these gases is not easy. Our telescopes can only gather tiny amounts of data from distant planets. Even if we find something that looks like a biosignature, it's hard to be certain. For example, methane can also be produced by geological processes, not just life. Could we mistake a lifeless planet for one teeming with life? On the other hand, what if we've already seen biosignatures but don't recognize them? Life on other planets might not look anything like life on Earth. Could we miss alien life simply because we don't know what to look for? As humans advance, we rely more and more on technology. Some scientists think advanced alien civilizations might do the same. Over time, they could even transition from biological beings to entirely technological ones. Post-biological civilizations might exist as artificial intelligences, living in virtual worlds or controlling robotic bodies. If so, they might have little interest in communicating with us. Could this explain why we haven't detected any signs of aliens? A post-biological civilization would also use energy and resources very differently from us. They might build massive structures to harvest energy from their stars, known as Dyson spheres. But so far, we haven't seen evidence of such structures. Does this mean they don't exist? Or are we simply looking in the wrong places? Another idea is that alien civilizations don't want to be found. They might be hiding to avoid detection by more advanced and potentially hostile civilizations. This idea is called the zoo hypothesis. According to this hypothesis, aliens might observe us from a distance, like animals in a zoo. They might be waiting for us to reach a certain level of technological or social development before making contact. But why would they wait? What are they hoping to see? Some people believe that aliens visited Earth in the past and left behind evidence, such as ancient structures or strange artifacts. But there's no solid proof of this. Most claims of ancient alien evidence can be explained by natural or human-made causes. Still, the idea raises an interesting question. If intelligent aliens did visit Earth long ago, would we be able to recognize their traces today? Could we be looking right at the evidence without realizing it? With all these possibilities, one thing is clear. The search for alien life is far from over. Are we looking in the wrong places, using the wrong methods? Or are we truly alone in this vast universe? The answers to these questions could redefine our understanding of life, the universe, and our place within it. As technology improves and we explore further, will we finally find the evidence we've been searching for? Or will the mystery of extraterrestrial life remain one of the universe's greatest unanswered questions? The universe is full of phenomena that defy our understanding. One such mystery is fast radio bursts. These are extremely short bursts of radio waves that come from deep space. They last only a few milliseconds, but release more energy in that time than the sun does in days. Scientists first discovered fast radio bursts in 2007. Since then, hundreds more have been detected, yet their origin remains unknown. Some bursts occur only once, while others repeat. This adds to the confusion about what causes them. Are they the result of natural processes? Or could they be something artificial? Some theories suggest fast radio bursts might come from highly magnetized neutron stars called magnetars. Others think they could be the result of black holes colliding or even signals from alien civilizations. Despite many observations, the true nature of fast radio bursts remains unclear. Another cosmic mystery is ultra-high-energy cosmic rays. These particles travel through space at nearly the speed of light and carry immense energy. They are so powerful that they can travel millions of light years across the universe. When they reach Earth, they interact with our atmosphere, creating showers of secondary particles. But where do they come from? The origins of these cosmic rays are still unknown. They could be produced by supermassive black holes, exploding stars, or even processes we have yet to discover. The problem is that these particles don't travel in straight lines. Magnetic fields in space bend their paths, making it nearly impossible to trace them back to their source. This has left scientists puzzled about what could generate such high-energy particles. Rogue planets add another layer of mystery to the cosmos. These are planets that don't orbit any star. Instead, they wander through space on their own. Scientists believe there could be billions of rogue planets in our galaxy alone. But how do they form? Some may have been ejected from their original star systems due to gravitational interactions. Others might have formed directly in the cold regions of space, far from any star. Without the light of a star, these planets are incredibly hard to detect. Yet their existence challenges our understanding of planetary formation. Rogue planets could also have hidden oceans beneath thick layers of ice, potentially providing habitats for life. But without a star, how could such life survive? These are questions that remain unanswered. Dark galaxies are another phenomenon that baffles astronomers. These are galaxies that contain very few stars or none at all. Instead, they are made mostly of dark matter and gas. They don't emit much light, making them extremely difficult to study. Scientists only discover dark galaxies indirectly by observing their effects on other galaxies. Their existence raises questions about how galaxies form and evolve. Why do some galaxies fail to produce stars? What role does dark matter play in shaping them? Dark galaxies could hold clues about the earliest stages of galaxy formation. But studying them is a challenge due to their faint nature. Advances in telescope technology may help us learn more about these mysterious objects in the future. The universe is vast and filled with enigmas that push the boundaries of our understanding. Each discovery brings new questions, revealing how much we still have to learn about the cosmos. As we continue to explore, these unknown phenomena remind us of the complexity and wonder of the universe. The ultimate fate of the universe is a question that has puzzled scientists for generations. There are several possibilities, and each one depends on the properties of the universe, like its overall shape, energy content, and the behavior of dark energy. One scenario is the heat death of the universe. In this future, the universe continues to expand forever. Over time, stars burn out, galaxies drift apart, and matter becomes spread so thin that no new stars can form. Eventually, even black holes evaporate through a process called Hawking radiation. What remains is a cold, dark universe where no processes can occur because there is no usable energy left. Another possibility is the Big Rip. This theory suggests that the universe's expansion might not just continue, but accelerate to the point where it tears everything apart. Galaxies, stars, and even atoms would eventually be ripped apart by the relentless expansion of space. The timing of this scenario depends on how the mysterious force of dark energy behaves. If dark energy grows stronger over time, it could overpower all other forces, leading to the Big Rip. However, scientists still don't fully understand dark energy, so this idea remains speculative. The role of black holes in the universe's fate is another area of interest. Black holes are regions of space where gravity is so strong that not even light can escape. Over time, they could play a significant part in recycling matter and energy in the universe. When stars and gas fall into black holes, they emit enormous amounts of energy in the form of radiation. Some theories suggest that black holes could eventually dominate the universe as the only remaining objects. They might also help us understand fundamental questions about space and time, as they are regions where the known laws of physics break down. There are also hypothetical scenarios that suggest the universe might not have an end at all. One idea is the concept of a cyclic universe. In this model, the universe goes through infinite cycles of expansion and contraction. After one universe ends, a new one could begin, starting with another Big Bang. This theory is appealing because it avoids the need to explain how the universe started from nothing. However, it requires mechanisms that scientists have not yet observed, such as how a universe would transition from contraction to expansion. Some theories propose that the universe could transition into a different state entirely. This idea is based on quantum mechanics, which suggests that the universe might exist in a state that is not completely stable. If a more stable state exists, the universe could suddenly decay into this new state in an event called vacuum decay. Such an event would completely reshape the laws of physics, destroying everything in the universe as we know it. This process would happen at the speed of light, meaning there would be no warning or way to stop it. Each of these scenarios highlights how much we still don't know about the universe and its ultimate destiny. To determine which of these possibilities is correct, scientists study the cosmos in great detail, using advanced telescopes and experiments. These efforts aim to uncover the nature of dark energy, the behavior of black holes, and the conditions that might lead to a cyclic universe or vacuum decay. The fate of the universe is a question that combines the mysteries of space, time, and physics, reminding us of how much there is yet to learn. In 2024, advancements in astronomy and space exploration continued to shed light on the mysteries of the universe. One of the most significant contributions comes from new telescopes equipped with cutting-edge technology. These telescopes are capable of capturing data from parts of the electromagnetic spectrum that were previously inaccessible. For example, radio telescopes with greater sensitivity allow scientists to detect signals from billions of light-years away. Infrared telescopes can peer through clouds of dust and gas, revealing stars and planets in their earliest stages of formation. These instruments provide clearer images of the universe, offering insights into phenomena like the behavior of galaxies and the distribution of dark matter. Artificial intelligence has also become a vital tool in space research. AI algorithms can process enormous amounts of data faster and more accurately than humans. For instance, AI is used to analyze data from telescopes, identifying patterns that might indicate the presence of planets, black holes, or other cosmic features. Machine learning models are also used to predict how stars evolve or how galaxies interact over time. This technology is helping scientists make discoveries that would have been impossible to detect manually, saving time and resources in the process. The James Webb Space Telescope continues to deliver groundbreaking results. Its ability to observe in the infrared spectrum allows it to study objects that are too faint or distant for other telescopes. In 2024, it has provided detailed observations of exoplanet atmospheres, giving scientists a better understanding of their composition. It has also captured images of the earliest galaxies that formed after the Big Bang, helping researchers piece together the history of the universe. These observations challenge some existing theories about how galaxies form and evolve, prompting scientists to reconsider their models. Another area of focus in 2024 is the search for signs of life beyond Earth. New missions are targeting planets and moons in our solar system that could harbor conditions suitable for life. For example, missions to icy moons like Europa and Enceladus aim to investigate their subsurface oceans, which could contain the chemical ingredients for life. On Mars, Rovers equipped with advanced instruments are analyzing soil and rock samples for traces of past or present life. Beyond our solar system, researchers are using telescopes to search for biosignatures, such as oxygen or methane, in the atmospheres of exoplanets. Emerging theories in cosmology are also gaining attention. Some scientists are exploring ideas that challenge the conventional understanding of dark matter and dark energy. For instance, alternative models suggest that these phenomena might not exist as separate entities, but could be explained by modifications to the laws of gravity. Other theories propose that dark energy might be linked to quantum fluctuations in empty space. These ideas are being tested through observations and experiments, pushing the boundaries of what we know about the universe. New methods for observing gravitational waves are another highlight of 2024. These waves, which are ripples in the fabric of space-time, are created by massive cosmic events like the collision of black holes. Advances in technology have made it possible to detect weaker signals from more distant sources. This allows scientists to study a wider range of events, such as the mergers of neutron stars or the collapse of massive stars. Gravitational wave astronomy is becoming a powerful tool for understanding the universe in ways that were not possible before. While these developments provide valuable insights, they also raise new questions. Observations from telescopes and experiments often reveal unexpected results, challenging scientists to refine their theories. For example, some galaxies appear to form stars at rates that current models cannot explain. Similarly, the distribution of matter in the universe sometimes deviates from predictions. These anomalies suggest that there is still much to learn about the underlying processes that govern the cosmos. Each breakthrough builds on previous knowledge while paving the way for future research. As technology advances and new methods are developed, the quest to understand the universe becomes more precise and far-reaching. This ongoing effort reflects humanity's drive to uncover the unknown, one observation at a time. The universe is a vast expanse, one that stretches beyond what the human mind can fully grasp. Its mysteries are as old as time itself, existing long before humanity began to ask questions about the stars and the space between them. These mysteries remind us of how small we are compared to the cosmos and how much we still do not understand about the reality we live in. The pursuit of knowledge about the universe has been a continuous journey, filled with discoveries that have reshaped our understanding of existence. Every question answered seems to lead to more questions, creating an endless cycle of exploration. The universe's immense scale challenges our ability to comprehend its structure and behavior. Distances are measured not in miles or kilometers, but in light years, emphasizing the vastness that separates celestial objects. Even the closest stars are so far away that their light takes years to reach us. This immense scale also means that what we observe is often a glimpse into the distant past. When we look at a galaxy millions of light years away, we are seeing it as it was millions of years ago. The universe is both a time machine and a reminder of how limited our perspective can be. The processes that govern the universe are equally complex. Stars form from clouds of gas, burn for billions of years, and then die, often in spectacular explosions. These stellar events create the elements that make up planets, living organisms, and everything else. The cycle of birth and death in the universe is a constant, yet it raises questions about the forces that drive it. Gravity, dark matter, and dark energy play roles in shaping the cosmos, but their exact nature remains a puzzle. Scientists continue to study these forces, hoping to uncover the laws that govern the universe's behavior. The search for extraterrestrial life adds another layer of mystery. The conditions that allow life to exist are rare, yet the universe is so vast that the possibility of life elsewhere seems likely. From the icy moons of our solar system to the distant exoplanets orbiting other stars, The search for life is a central focus of modern astronomy. The discovery of even the simplest forms of life beyond Earth would be one of the most profound findings in human history. It would confirm that we are not alone and that life can emerge in places far removed from our planet. Technological advances have made it possible to explore the universe in ways that were unimaginable just decades ago. Telescopes on Earth and in space provide detailed images of distant galaxies, nebulae, and star clusters. Spacecraft have visited planets, moons, and even comets, sending back data that deepens our understanding of the solar system. Yet, even with these tools, much of the universe remains hidden. Some regions are obscured by clouds of gas and dust, while others are so far away that their light has not yet reached us. The limitations of our technology remind us of how much there is still to discover. The study of time and its connection to the universe is another area of great intrigue. Time flows in one direction, from past to future, but the reasons for this are not fully understood. Phenomena like time dilation, where time slows down under certain conditions, show that time is not as straightforward as it seems. The relationship between time and space, as described by Einstein's theory of relativity, is key to understanding the universe. Yet, questions about the origin of time and its ultimate nature remain unanswered, highlighting the complexity of the cosmos. The concept of infinity also challenges our understanding. Is the universe infinite, or does it have a boundary? If it does have a limit, what lies beyond it? These questions touch on the fundamental nature of reality itself. Infinity is a concept that defies human experience, yet it is central to many theories about the universe. Whether we are dealing with the infinite size of space or the endless possibilities of parallel universes, the idea of infinity pushes the boundaries of what we can comprehend. The mysteries of the universe are not just scientific questions. They're also deeply philosophical. They force us to confront our place in the cosmos and consider what it means to exist. Why is there something rather than nothing? What is the purpose of the universe? If it has one, these are questions that science cannot answer, but that continue to inspire curiosity and wonder. They remind us that the search for knowledge is not just about finding answers, but about asking the right questions. Exploration is an essential part of human nature. From ancient astronomers who first mapped the stars to modern scientists who study the universe with advanced tools, the desire to understand the cosmos has always been a driving force. This desire is what pushes us to look beyond our planet, to send spacecraft to other worlds, and to build telescopes that can peer into the depths of space. The discoveries we make are not just scientific achievements. They are milestones in humanity's journey to understand its place in the universe. The universe is both a source of answers and a source of questions. It challenges us to think beyond our everyday experiences and to imagine possibilities that seem beyond reach. It is a reminder of the complexity of reality and the limits of our understanding. But it is also a testament to human ingenuity and curiosity. The quest to uncover the mysteries of the cosmos is one of the greatest endeavors of our species, a journey that continues to inspire and unite us in the pursuit of knowledge. Reality is not as solid as it seems. Beneath the surface of what we call existence lies an intricate and beautiful web of rules. A set of principles so strange and counterintuitive that they defy the very logic we rely on in our everyday lives. Imagine a world where information is not just something we store on hard drives or write in books, but is a fundamental, physical, and a primary building block of reality itself. A world where the basic units of data are not fixed, definite ones and zeros, but are fluid, shimmering, and probabilistic entities, existing in a ghostly superposition of multiple states at once. This is a realm where the very act of observation, of looking at something, changes the nature of what is there. It is a world where two particles, separated by the vast, cold emptiness of galaxies, can be so deeply and mysteriously connected that the actions of one instantly, and without any apparent communication, affect the other. It is a world where a simple measurement can erase a universe of possibilities, collapsing the limitless into the defined, the potential into the actual. This is not the realm of science fiction, of fantasy, or of mystical speculation. This is the world as it is described by our best and most fundamental theory of nature, the theory of quantum mechanics. It is the foundation of the universe itself. For centuries, the clockwork, predictable order of classical physics painted a picture of a reality that was, at its core, understandable and intuitive. But as we have learned to probe deeper into the heart of matter, as our experiments have become more sensitive and our theories more sophisticated, we have found that the smallest scales of nature do not behave as our classical instincts tell us they should. They operate on a different logic, a different set of principles, a set of principles so bizarre that even Albert Einstein, one of the great architects of modern physics, struggled to accept them, famously dismissing one of its key features as spooky action at a distance. What if information is not just an abstract concept that we use to describe the world, but is the very scaffolding upon which reality is built? What if the universe is, in some deep and fundamental sense, a cosmic algorithm, a vast quantum computation that is constantly processing the fabric of existence itself? This is a radical and profound idea, one that is emerging from the confluence of physics, computer science, and information theory. It suggests that the its of the physical world, the particles, the fields, the forces, are all, at their core, manifestations of bits of quantum information. Yet, for all its strangeness and its deep philosophical mystery, the world of quantum information is not just a theoretical curiosity. It is a field that holds the potential to revolutionize our technology, to create new forms of computation, of communication, and of security that were previously unimaginable. It promises to give us unbreakable encryption, to build computers that can solve problems that are intractable for even the most powerful classical supercomputers, to create sensors of unprecedented precision. But could the strange and beautiful rules of quantum information also hold the answers to questions that are even more profound? Could the ultimate nature of reality itself be, at its core, an elaborate and beautiful interplay of quantum codes? Could consciousness, could life, could the very structure of space-time be emergent properties of an underlying informational reality? These are the questions that are driving the next great revolution in our understanding of the cosmos. The deeper we look, the stranger it becomes. The quantum world is a realm where our conventional, classical intuition crumbles into dust. And with it, our understanding of something as seemingly straightforward as information undergoes a profound and radical transformation. In classical physics, information is an abstract and secondary concept. It is something that we use to describe a physical system. It is the bits stored on a hard drive, the words written on a page, the positions and velocities of a set of particles. The information describes the reality, but it is not the reality itself. But in the quantum domain, this clear distinction between the physical system and the information it contains begins to dissolve. Quantum information takes on a physical and even primary identity. This physicality changes the very way we define and process information, endowing it with a strange and powerful set of new properties. Imagine a simple, classical bit of information, like the outcome of a coin flip. It is binary. It can be either heads or tails, a 1 or a 0. But a quantum bit, or qubit, the fundamental unit of quantum information, is not so constrained. Thanks to the principle of superposition, a qubit can be a 0, a 1, or most remarkably, a ghostly, probabilistic blend of both at the same time. It is like a coin that is not heads or tails, but is spinning forever in a shimmering blur of both possibilities, until the moment it is measured. This non-binary nature of the qubit, its ability to exist in a continuous spectrum of states, adds an incredible complexity and power to the very notion of information. It means that a quantum system can store and process a vastly greater amount of information than its classical counterpart. This is not just a quantitative difference, it is a qualitative one. Quantum mechanics challenges the very deterministic perspective that underpins classical physics. A classical system, like a set of billiard balls on a table, is predictable. If you know the initial positions and velocities of all the balls, you can, in principle, calculate their entire future trajectory with perfect accuracy. But a quantum system is fundamentally, irreducibly probabilistic. You can never know its future with certainty. You can only know the probabilities of the different possible outcomes. This means that a quantum system is not just a matter of having enough data. It demands a complete reevaluation of how we interact with the universe, of the very nature of knowledge itself. Information, in this quantum picture, is not just a passive record of a pre-existing reality. It is an active, dynamic, and participatory entity, something that is woven into the very fabric of physical law. The theory of quantum mechanics suggests that all physical systems are, at their core, carriers of information. But this is not just descriptive, classical information. Quantum information has a set of strange and unique properties that set it apart. Properties that enable transformations and processes that are simply impossible in the classical world. Take, for a moment, the concept of measurement. What actually happens when we look at a quantum system? This question strikes at the very heart of the measurement problem, one of the most contentious and deeply debated puzzles in all of quantum mechanics. As we have seen before it is observed, a quantum particle exists in a superposition of all its possible states. It is like an unread book, a book that contains every possible story, every possible narrative, all at the same time. The moment we read the book, the moment we make a measurement, we seem to force it to choose a single, definite story. The superposition collapses, and one of the many possibilities becomes the single, actual reality. But does this act of measurement represent the creation of information, or are we merely revealing a piece of a pre-existing, but hidden, reality? The paradox deepens when we consider the nature of quantum states themselves. In the classical world, you can measure a property of a system, like the temperature of a cup of coffee, without fundamentally changing the system itself. But in the quantum world, this is not always the case. There are certain quantum states that cannot be fully known without destroying them. The very act of gaining information about the system can irrevocably alter it. Observation is not a passive act. It has a real physical cost. This forces us to rethink the very concept of truth or fact. Imagine two scientists trying to understand the state of a single electron. One scientist decides to measure its position with great precision. The other decides to measure its momentum. According to the uncertainty principle, they cannot both get a precise answer. The first scientist's measurement of the position makes the electron's momentum fundamentally uncertain. The second scientist's measurement of the momentum makes its position fundamentally uncertain. They are not just getting different, incomplete pieces of a single, objective picture. They are, in a sense, creating two different and mutually exclusive realities through their choice of measurement. The complementary nature of quantum systems, the fact that certain properties exist in a trade-off, ensures that our knowledge of the quantum world is always and fundamentally partial. It is not a limitation of our instruments. It is a built-in feature of reality. From this inherent uncertainty, we move to an even stranger and more profound quantum feature entanglement. When two or more particles become entangled, their individual quantum states are no longer independent. They merge into a single, shared state, a single wave function that describes the entire system, regardless of the distance separating the particles. Einstein, as we know, dismissed this as an eerie coincidence, a spooky action at a distance. But today, we know that entanglement is a real physical phenomenon. It binds particles together like invisible, non-local threads stretching across the vastness of the cosmos. Through this strange connection, one particle seems to know the state of its partner instantly, no matter how far apart they are. The measurement of one immediately influences the state of the other. The implications of this quantum entanglement for the nature of information are profound and revolutionary. It opens the door to technologies that were once the sole domain of science fiction: quantum teleportation, for example, is no longer a fantasy. It is a real, experimentally verified phenomenon. When two particles are entangled, it is possible to teleport the quantum state of a third particle onto one of the entangled pair, a process that effectively transfers the information across space without physically moving any matter. While this process does not allow for faster-than-light travel, the classical information needed to complete the teleportation process must still be sent at or below the speed of light. It is a phenomenon that fundamentally redefines our understanding of how information can be communicated. But the quantum world does not just offer new possibilities for information, it also imposes strict and beautiful new limits. The no-cloning theorem, a fundamental principle of quantum mechanics, states that it is impossible to create an identical, independent copy of an arbitrary, unknown quantum state. You cannot simply photocopy a qubit in the same way you can photocopy a classical bit. This is a profound and important feature of the quantum world. It ensures that quantum information has a kind of privacy and integrity that classical information lacks. It is the physical basis for the security of quantum cryptography. It also tells us something deep about the nature of reality. The universe, it seems, does not allow for perfect replication. Each quantum system is, in a sense, unique and unreproducible. The entangled pairs themselves carry their own unique measure of informational complexity, a quantity known as entanglement entropy. This entropy is a measure of the shared, non-local information between the particles, the degree of their interconnectedness. And it is this entanglement entropy that explains why. Despite the seeming magic of teleportation, entanglement cannot be used to send free, unlimited, and faster-than-light classical information. There are deep and beautifully consistent rules that govern the flow of information in the quantum world. Underpinning all of these strange and wonderful principles is the ever-present hum of the uncertainty principle. Heisenberg's revolutionary assertion that not all properties of a particle can be known with perfect precision at the same time. This is not just a limit on our knowledge, it is a fundamental feature of the information content of the universe itself. It places a cap on how much useful, classical information can be extracted from any quantum system at a given time. To encode and retrieve data in the quantum world requires a series of deliberate trade-offs, a kind of delicate balancing act that is dictated by the fundamental, complementary nature of reality. The complementarity principle, the idea that certain properties, like a particle's wave-like and particle-like nature, are mutually exclusive but equally necessary for a complete description, is the ultimate expression of this trade-off. You can ask a wave question, or you can ask a particle question, but you can never ask both at the same time. The information you gain about one aspect of reality necessarily costs you clarity in another. This is a profound departure from the classical worldview, where perfect, complete knowledge seems, at least in principle, to be attainable. In the quantum world, knowledge is inherently and beautifully incomplete. All of this complexity, all of this strangeness raises a deep and compelling question about the ultimate nature of reality. Is the universe at its core an informational entity? What if the physical world is not the fundamental reality, but is an emergent phenomenon, a manifestation of a deeper underlying quantum computation? This is not just an abstract philosophical speculation. It is an idea that is gaining traction in the world of theoretical physics. The process of decoherence, for example, can be seen as a kind of bridge between the quantum and classical worlds of information. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate, superpositional, and entangled nature. The quantum information, the qubitness of the system, is not destroyed, but is rapidly spread out and dissipated into the vast number of degrees of freedom of the environment, becoming, for all practical purposes, irretrievable. This process is what explains why we do not see macroscopic objects like cats in a state of superposition. It is what allows the definite, classical world of our experience to emerge from the fuzzy, probabilistic world of the quantum. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. The idea of quantum information as being primary suggests that our universe might not just obey physical laws. It might embody them as a form of computation. The evolution of the universe, from the Big Bang to the present day, could be seen as a single, vast, and ongoing quantum computation. A process that is constantly processing information and creating new, more complex structures. In this view, particles are not just things, they are carriers of quantum information, data packets that are navigating a vast, cosmic computational architecture. This is a vision that transcends the classical idea of a universe composed of inert matter and forces. It imagines a universe that is, in a very real sense, alive with information. A universe that is constantly thinking, constantly computing its own reality into existence. And this vision has real, practical applications, particularly in the field of cryptography. The very properties of quantum information that make it so strange: superposition, entanglement. The no-cloning theorem are the same properties that make it the basis for a new and revolutionary kind of security: quantum cryptography, and specifically quantum key distribution, is a technology that uses the principles of quantum mechanics to create a provably secure communication channel. By encoding a secret key in the quantum states of single photons and sending them over an optical fiber, two parties can establish a shared, random key that can be used to encrypt and decrypt their messages. The security of this system is guaranteed by the laws of physics. Any attempt by an eavesdropper to measure the photons will inevitably disturb their quantum state, a disturbance that can be immediately detected by the legitimate users. The randomness inherent in quantum measurement also provides a source of true, unpredictable randomness, which is a crucial ingredient for strong encryption protocols. As we look to the future, the development of a quantum internet, a global network that can transmit and process quantum information, could revolutionize not just our security, but our entire information infrastructure. It would be a network that is not just faster or more efficient, but is fundamentally different, a network that is built on the strange and beautiful logic of the quantum world itself. The journey into the heart of quantum information is a journey that is reshaping our deepest understanding of reality. It is a journey that ties together the abstract concepts of measurement, uncertainty, and entanglement, and reimagines them as the constituent parts of a single, unified, Informational framework. And it is a framework that does not just describe reality. It actively determines it. From the security of our most sensitive communications to the most profound and existential questions about the nature of the cosmos. Quantum information is shifting our perspective in deep and powerful ways. Could this be the true foundation of reality? Or is it merely a window into an even deeper, more mysterious layer of existence that is still awaiting our discovery? The tantalizing potential of this new science ensures one thing: this quantum narrative is far, far from over. From the relentless march of entropy and thermodynamics to the deepest and most profound mysteries of quantum mechanics, the concept of information serves as a crucial unifying thread, weaving its way through the vast and varied phenomena that define our physical world. To truly understand how profound and fundamental this concept is, we must first consider the intimate and beautiful relationship between information and entropy, a relationship that is at the very heart of the second law of thermodynamics. We see the effects of this law everywhere: the gradual crumbling of a mountain, the slow fading of a cherished memory. The inevitable cooling of a cup of coffee. Entropy is the universe's great, inexorable tendency towards disorder, towards a state of greater probability and lesser structure. It is the physical basis for the arrow of time. But here is where the story takes a fascinating turn. Information, in its purest, most fundamental sense, is a measure of order, of structure, of reduced uncertainty. When a physical system is in a highly ordered, low-entropy state, like a perfectly arranged deck of cards, we have a great deal of information about it. As the system evolves towards a state of higher entropy, as the cards are shuffled, this information is not destroyed, but is dispersed, becoming harder to access. The act of gaining information about a system, of making a measurement, is an act that can, at least locally, reduce its entropy, an act that brings order out of chaos. This beautiful and intricate dance between the disorder of entropy and the order of information was first given a rigorous mathematical form by the American engineer and mathematician Claude Shannon in his groundbreaking work on information theory in the 1940s. Shannon's work, which was originally designed to understand the limits of communication over noisy channels, provided a precise mathematical definition of information in terms of the reduction of uncertainty, and showed that it was deeply and formally connected to the concept of entropy in thermodynamics. This connection was deepened and made more physical by the work of the physicist Rolf Landauer in the 1960s. Landauer's principle, a cornerstone of the physics of information, established a fundamental link between the abstract, logical operation of computation and the concrete, physical world of energy and heat. Landauer showed that the erasure of a single bit of information from a computational system is not a purely logical act. It has a real physical cost. It must, by necessity, be accompanied by the generation of a small, but unavoidable, amount of heat, an increase in the entropy of the environment. This principle established, once and for all, that computation is not an abstract, disembodied process. It is a physical process, bound by the very same thermodynamic laws that govern the behavior of steam engines and chemical reactions. The metaphysical concept of information was thereby firmly and irrevocably tied to the tangible, material reality of the universe. This intimate relationship between information, entropy, and energy is beautifully illustrated in one of the most famous and enduring thought experiments in the history of physics: Maxwell's demon. In the 19th century, the physicist James Clerk, Maxwell imagined a tiny, intelligent being, a demon, who could control a tiny, frictionless door in a partition that divides a box of gas into two chambers. By observing the individual gas molecules, the demon could open the door to let the fast-moving, hot molecules pass into one chamber, and the slow-moving, cold molecules pass into the other. Over time, the demon could create a temperature difference between the two chambers, seemingly decreasing the entropy of the system in violation of the second law of thermodynamics. This paradox puzzled physicists for over a century. The solution, which was finally clarified in the 20th century with the development of information theory, lies in the information processing that the demon must perform. To do its job, the demon must first measure the velocity of each molecule, a process that requires the acquisition of information. It must then store this information in its memory. And finally, it must erase its memory to make room for the next measurement. And it is this act of erasing information that, according to Landauer's principle, must generate entropy, an amount of entropy that is at least as great as the entropy that was seemingly reduced by sorting the molecules. The second law is saved, but at a price. The thought experiment demonstrates, in a beautiful and profound way, how inseparable information is from the physical processes it describes. Information is not a ghostly, non-physical entity. It has a real physical substrate, and its manipulation has real physical consequences. This principle extends to the largest scales of the cosmos. The flow of information in our universe is fundamentally constrained by the laws of relativity. The speed of light is not just the maximum speed at which matter and energy can travel. It is the maximum speed at which information can be transmitted. This cosmic speed limit is what safeguards the principle of causality, the fundamental idea that a cause must always precede its effect. It ensures that the temporal order of events is preserved, that the past cannot be changed by the future. The very structure of space-time, with its fixed and universal speed of light, is a structure that is designed to regulate the flow of information, and it is at the intersection of relativity and information that we find one of the deepest and most challenging puzzles of modern physics: the black hole information paradox. When matter, with all its rich and complex information, falls into a black hole, it seems to be lost to the universe forever, trapped behind the one-way membrane of the event horizon. And when the black hole eventually evaporates through Hawking radiation, that radiation appears to be purely thermal, random, and devoid of any of the information that originally fell in. This would represent a fundamental violation of the quantum mechanical principle that information can never be truly destroyed. The resolution of this paradox is thought to lie in the subtle, quantum correlations and entanglements within the outgoing Hawking radiation, a solution that would require a deep and beautiful synthesis of quantum mechanics, general relativity, and information theory. Beyond the realms of classical physics, thermodynamics, and relativity, the role of information becomes even more central when we consider the dynamic, creative, and evolutionary processes of the universe. Despite the second law's relentless push towards greater disorder, the universe is not a uniform, featureless soup of entropy. On the contrary, it is filled with islands of astonishing and beautiful complexity, the intricate structures of galaxies, the fiery hearts of stars, the delicate and purposeful machinery of living organisms. These ordered structures are not a violation of the second law. They are a consequence of it. They are what the Nobel laureate Ilya Prigogine called dissipative structures, open systems that maintain their internal order by importing energy from their environment and exporting entropy. A star, for example, is a highly ordered system that maintains its structure by consuming the low-entropy fuel of hydrogen in its core and radiating high-entropy heat and light into the surrounding space. Life is the ultimate example of this process. A living organism is an island of incredible, localized order, a system that actively works to maintain its structure and to create new knowledge, all while increasing the overall entropy of the universe around it. The process by which these complex, ordered structures emerge is known as self-organization, And information is the silent guiding architect of this process. The flow of energy through a system is not enough to create complexity. There must also be an informational blueprint, a set of rules or constraints that guides the self-organizing process. In the formation of a snowflake, this blueprint is provided by the crystalline structure of water and the laws of thermodynamics. In the formation of a galaxy, it is provided by the laws of gravity and the initial density fluctuations in the early universe. And in a living organism, it is provided by the rich and unimaginably complex information encoded in the DNA molecule. This can be understood through the statistical interpretation of entropy, first developed by Ludwig Boltzmann. Boltzmann showed that the entropy of a system is related to the number of possible microscopic arrangements of its constituent parts that correspond to the same macroscopic state. A disordered, high-entropy state, like a shuffled deck of cards, is a state that can be realized in a vast number of different ways. An ordered, low-entropy state, like a deck of cards arranged in perfect numerical and suit order, is a state that can be realized in only one way. Information, in this picture, is what allows a system to find its way to these rare, improbable, and highly ordered states. The information in the DNA molecule, for example, guides the complex process of protein synthesis, ensuring that the right amino acids are assembled in the right order to create the functional machinery of the cell. It is a process that carves out a tiny, highly ordered path through a vast, chaotic landscape of possibility. The arrow of time, then, is a story of two competing tendencies. On the one hand, there is the relentless universal drive towards greater entropy, towards disorder and heat death. But on the other hand, there is the creative, local, and information-driven process of self-organization, a process that builds islands of exquisite and beautiful complexity against this cosmic tide. Life is the most remarkable and poignant expression of this creative countercurrent. It is a process that thrives by absorbing energy and processing information, a process that creates pockets of meaning and purpose in a universe that is, on the whole, becoming more meaningless and purposeless. And at the heart of this creative process lies the mysterious and powerful role of information. The principles of information are not just at play in the grand cosmic drama of stellar and biological evolution. They are also at the heart of the strange and beautiful world of quantum mechanics, at the smallest scales of reality. The very act of gaining information about a system, the act of measurement, is a process that fundamentally changes the state of that system. This is the basis of the thermodynamics of measurement, a field that explores the deep and intimate connection between information, entropy, and the quantum world. When we measure a property of a quantum particle, like its spin or its position, we are extracting information from it. But this is not a passive act. The measurement process itself is an irreversible, entropy-increasing interaction. It is the process by which the ghostly, probabilistic world of quantum superposition is collapsed into the definite, singular reality of our classical experience. The process of decoherence is the mechanism by which this happens. A quantum system is never truly isolated. It is always interacting, however subtly, with its environment. The information about its delicate superpositional state leaks out into the vast number of degrees of freedom of the surrounding world, becoming, for all practical purposes, irretrievably lost. This is what gives the quantum world its classical appearance. The definite, stable reality we perceive is a consequence of the constant entropic loss of quantum information into the environment. Perhaps one of the most exciting and forward-looking applications of these ideas is in the field of quantum computation. A classical computer processes information one logical step at a time, but a quantum computer, by harnessing the principle of superposition, can explore a vast number of computational paths simultaneously. This quantum parallelism gives it the potential to solve certain problems, like factoring large numbers or simulating complex quantum systems at a speed that is exponentially faster than any classical machine. This is a technology that could revolutionize science, medicine, and artificial intelligence. And as we look to the future, the frontier of information physics hints at even more radical and profound insights. Some researchers, in their quest for a theory of quantum gravity, have proposed that the very fabric of spacetime may be, at its core, an informational construct. The holographic principle, for example, theorizes that all the information contained within a three-dimensional volume of space can be completely described by the information encoded on its two-dimensional boundary, like a hologram. If this is true, it would mean that information is not just a property of reality. It may be the very substance of reality itself. Furthermore, a deeper understanding of the thermodynamics of information could lead to a new generation of hyper-efficient technologies. By leveraging principles like Landauer's limit, we might one day be able to build computational and communication systems that operate at the absolute physical limits of energy efficiency. A future where our technological progress is guided not by the raw consumption of energy, but by the subtle and intelligent manipulation of information. And so, as our journey through the world of information comes to a close, we are left with a profound and tantalizing question. What if the universe itself is, at its most fundamental level, a vast, interconnected, and self-organizing field of information? If so, then every star, every planet, every living being would be a constituent part of a grand cosmic informational matrix, a matrix that is constantly evolving, constantly learning, constantly creating new forms of order and complexity. Understanding this deeper, informational reality might not just unlock the next technological revolution. It might also reveal our true place in the intricate and beautiful dance of order, chaos, and knowledge. Information, once seen as a mere abstract description of the world, now emerges as the very scaffolding upon which the universe is built. From the inexorable increase of entropy to the creative process of self-organization, from the strange logic of the quantum world to the grand evolution of the cosmos. It is the thread that illuminates our path towards a deeper and more unified understanding of what energy and matter alone could not explain. As we continue to probe the mysteries of information and its physical manifestations, one thing becomes clear: the story of the universe is not just about what it is made of, but about what it communicates. And in learning to read this cosmic message, we are not just deciphering the secrets of the universe. We are, in a very real sense, discovering our own. Life, at its very essence, can be understood as a profoundly sophisticated and ancient information processing system. Every single cell in your body, from the neurons in your brain to the muscle fibers in your heart, operates like a tiny, powerful, and exquisitely designed biological computer, constantly handling a vast and complex flow of information to sustain the miracle of your existence. And the source code for this incredible biological software is not written in silicon, but in the elegant double helix structure of the DNA molecule. DNA is not just a chemical, it is nature's own time-tested programming language, a biological script that has been written, edited, and refined over the course of nearly 4 billion years of evolution. This single, remarkable molecule, present in almost every cell of your body, contains the complete set of instructions, the architectural blueprint, that guides everything from the division of your cells to the synthesis of the proteins that are the workhorses of your biological machinery. It is a vast and ancient library of life, a library where every book is a gene, and every chapter contains a piece of the accumulated evolutionary wisdom of your ancestors. The process of evolution itself can be seen as the ongoing editing and refinement of this great genetic library. Through the random, mutational process of trial and error, life is constantly experimenting with new editions of its own chapters. Random changes in the genetic information, mutations, recombinations, and the more subtle epigenetic modifications that can be influenced by the environment create a constant stream of new variations. Natural selection then acts as a harsh, but ultimately creative, editor. Those variations that happen to provide a survival or reproductive advantage in a particular environment are preserved and passed on to the next generation, while those that do not are discarded. This process, repeated over countless generations, is not just a random walk through the space of possibility. It is a powerful optimization algorithm, a process that allows life to learn, to adapt, and to accumulate an ever-growing repository of knowledge about how to thrive in an often hostile and unpredictable universe. These principles of biological information processing are not just metaphorical. They are deeply and formally connected to the mathematical principles of information theory, a field that was originally developed to understand the transmission of data in man-made communication systems. The rules of information fidelity, of redundancy, of error correction, are just as relevant to the replication of a DNA molecule as they are to the transmission of a digital file over the internet. The genetic code, for example, is brimming with built-in safety mechanisms. It has a degree of redundancy, where multiple different codons can code for the same amino acid, providing a buffer against some mutations. And our cells have evolved a sophisticated and complex machinery of DNA repair enzymes, molecular proofreaders that constantly scan the genome for errors and correct them, ensuring that the vital instructional information is preserved with an incredible degree of fidelity. But this stability does not stifle evolution. On the contrary, it provides the stable, reliable foundation upon which the creative process of variation and selection can occur. The story of life's information processing continues in the intricate, dynamic, and beautiful networks of communication that exist within and between our cells. The flow of information from the genetic archive of the DNA to the functional machinery of the cell is a marvel of molecular engineering. In a process called transcription, a segment of the DNA is copied into a messenger RNA molecule. This mRNA molecule then travels out of the nucleus and into the cytoplasm, where, in a process called translation, its sequence is read by a molecular machine called a ribosome, which assembles a specific protein, amino acid by amino acid, according to the genetic instructions. This is the central dogma of molecular biology, the fundamental flow of information from DNA to RNA to protein. And it is a process that is happening trillions of times a second in your body right now. The way our cells process this vast amount of data is a masterclass in decentralized, distributed computing. There is no central processing unit, no single brain of the cell. Instead, the cell is a complex, self-organizing network of interacting molecules, a symphony of biochemical signals where each part is in constant communication with the whole, allowing the cell to respond and adapt to its constantly changing environment in a remarkably efficient and robust way. The role of information in building the complexity of life becomes even more apparent when we consider the great evolutionary transition from single-celled organisms to multicellular life. This was a leap that required a complete and radical restructuring of how biological information is stored, processed, and transmitted. Multicellular organisms had to invent new ways to coordinate the functions of billions and even trillions of interconnected cells, to ensure that they all work together for the good of the whole. The emergence of the nervous system was a key innovation in this process. The neural network of an animal is an advanced biological supercomputer, a system that is dedicated to processing the vast amount of sensory information from the environment. to driving complex behaviors, and to fostering the process of decision-making. But life's ingenuity in information processing is not limited to the top-down control of neural systems. At the other end of the biological spectrum, we find phenomena like horizontal gene transfer in bacteria, a process where single-celled organisms can directly exchange genetic information with each other, even across species boundaries. It is a kind of biological internet, a peer-to-peer network that allows for the rapid spread of useful genetic innovations, like antibiotic resistance, through the microbial world. These different strategies, the centralized processing of a nervous system and the decentralized network of horizontal gene transfer, are both powerful examples of how life, at every scale, is constantly experimenting with new and more efficient ways to handle the challenges of evolutionary adaptation. Adaptation itself, at its very core, is a process of changing how information is processed and utilized. Organisms are not passive slaves to their genetic programming. They are active, learning systems that are constantly adjusting their internal and external information strategies in response to the pressures of their environment. The process of learning and memory, for example, which is so highly developed in species like birds and mammals, is a powerful adaptive mechanism. It allows an organism to store information about its past experiences, the location of a food source, the presence of a predator, and to use that information to make better, more informed decisions in the future. The environment itself acts as a constant stream of feedback, a set of data that shapes and refines these learning processes, forcing life to operate like a complex, adaptive algorithm that is constantly working to maximize its efficiency and its chances of survival. The influence of information becomes even more profound and fascinating when we consider how these evolutionary processes extend beyond the realm of biology and into the realm of culture and cognition. The evolution of language in human beings, for example, was not just the development of a new way to make sounds. It was a revolutionary leap in the technology of information storage and transmission. Language allowed knowledge to be accumulated, shared, and built upon across generations. A process that is far more rapid and powerful than the slow generational transfer of genetic information. Language is, in a very real sense, a form of externalized biological information. A mimetic code that has allowed human culture to evolve and adapt at a breathtaking pace. And over the course of our history, we have continued to extend the principles of biological information processing into our artificial systems, from the invention of writing and the printing press to the development of the digital, computational marvels that define our modern world. Even the nature of intelligence itself is deeply and inextricably tied to the way that organisms process and utilize information. The increased complexity of the neural connections in the brains of so-called intelligent species is a direct reflection of the growing need to analyze, to store, and to respond to an ever-increasing amount of data from a complex and ever-changing environment. Human cognition, and by extension, human intelligence, has co-evolved with these powerful information processing abilities. To be intelligent is not just to be able to think, it is to be able to efficiently acquire, to analyze, to synthesize, and to translate information into effective, purposeful action. Understanding these deep and beautiful connections between biology, information theory, and evolution paints a new and compelling portrait of life. It is a narrative of constant change, of relentless refinement, and of beautiful adaptation. A narrative in which information lies at the very heart of everything. Life does not evolve randomly. It evolves systematically, constantly finding new and more ingenious ways to process, to store, and to leverage its vast and growing informational wealth in order to thrive against the odds. The evolutionary journey of life, from the first self-replicating molecule to the complex, global civilization of our own species, is not just a story of the survival of the fittest. It is the story of the survival of the most informationally adept. And as we stand at this unique moment in history, as we begin to create new, artificial forms of intelligence, we are not just continuing this evolutionary process. We are, perhaps, on the verge of accelerating it in ways that are both thrilling and deeply, profoundly unsettling. The story of life is the story of information, and it is a story that is far, far from over. The quantum phenomenon of entanglement is not just a strange and counterintuitive curiosity of the subatomic world. It is an experimentally verified reality, a feature of the cosmos that forces us to fundamentally reevaluate our classical notions of space, of distance, and of connection. It is the discovery that two or more particles can share a single, unified quantum state, a relationship so profound and immediate that it seems to challenge the very locality of reality. The idea that objects can only be influenced by their immediate surroundings. But this is where the story gets even stranger. The concept is so bizarre that it deeply troubled even Albert Einstein, who, along with his colleagues Boris Podolsky and Nathan Rosen, famously labeled it spooky action at a distance. In their 1935 paper, they constructed the EPR paradox, a thought experiment designed to show that the predictions of quantum mechanics were so strange that the theory must be incomplete. They argued that if quantum mechanics was right, then particles could seemingly communicate faster than the speed of light, a clear violation of one of the most fundamental principles of his theory of relativity. For Einstein, this spookiness was a sign that there must be some local hidden variables, some unknown properties that the particles carried with them that were predetermining the outcomes of the measurements, thus preserving the comforting classical notion of locality. For decades, this was a philosophical debate, but in the 1960s, the physicist John Bell, in a stroke of brilliant insight, formulated a mathematical theorem, now known as Bell's theorem, which provided a way to experimentally test the predictions of quantum mechanics against any possible local hidden variable theory. Bell's theorem, and the numerous increasingly precise Bell test experiments that have been performed in the decades since, have delivered a stunning and unambiguous verdict. The inequalities derived by Bell have been overwhelmingly violated, time and time again, confirming the non-local predictions of quantum mechanics and ruling out the possibility of any local hidden variable explanation. The spooky action is real. The universe is, in some deep and fundamental way, non-local. This does not mean that we can use entanglement to send faster-than-light signals and violate causality. But the underlying instantaneous connection is undeniably there. It tells us that our intuitive picture of a universe made up of separate, independent objects is an illusion. The answer to how this happens lies in the strange nature of quantum measurement. When we observe or measure one of the entangled particles, its wave function, the cloud of its possibilities, collapses and it settles into a definite state. And because the two particles are part of a single, unified quantum system, this collapse is not a local event. The entire entangled wave function collapses at once, and this means that the state of the distant, unmeasured partner is also instantly determined. This phenomenon of wave function collapse raises profound questions about the role of the observer in defining reality. Is the universe fundamentally deterministic, with the collapse just revealing a pre-existing state? Or does the act of observation itself play a creative role in shaping the outcome? This brings us to the concept of decoherence, a process that helps to bridge the gap between the strange, superpositional world of the quantum and the definite, classical world of our experience. Decoherence explains how a quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence, its ability to be in a superposition of states. The information about the superposition leaks out into the environment, making it practically impossible to observe. This is why we do not see macroscopic objects in a state of superposition. But decoherence does not fully solve the measurement problem, it just pushes it back. Different interpretations of quantum mechanics. From the traditional Copenhagen interpretation to the radical many worlds interpretation, continue to wrestle with this deep, conceptual riddle. The profound implications of quantum entanglement extend far beyond the realm of theoretical physics and into the world of revolutionary new technologies. The strange, non-local connection between entangled particles is not just a philosophical puzzle. It is a powerful new resource that we are just beginning to learn how to harness. Take, for example, the field of quantum cryptography. The security of our current classical communication systems is based on the computational difficulty of solving certain mathematical problems, like factoring large numbers. But a sufficiently powerful quantum computer could, in principle, solve these problems easily, rendering much of our current encryption obsolete. Quantum cryptography offers a new and fundamentally more secure paradigm. By using entangled photons to create a secret, shared key between two parties, a process known as quantum key distribution, it is possible to create a communication channel whose security is guaranteed not by computational complexity, but by the fundamental laws of physics. Any attempt by an eavesdropper to intercept and measure the photons will inevitably disturb their entangled state, a disturbance that can be immediately detected by the legitimate users. It is a system that is, in principle, unhackable. Similarly, the phenomenon of quantum teleportation, once the stuff of science fiction, is now a routine, if still small-scale, laboratory experiment. It uses the principles of entanglement to transfer the complete quantum state of a particle from one location to another, without physically moving the particle itself. This is not the beaming up of Captain Kirk, but it is a revolutionary new way to think about the transmission of information, a process that could one day be the foundation of a quantum internet, a global network that can transmit and process quantum information. And it is in the field of quantum computing that the power of entanglement is most fully realized. A classical computer processes bits of information that are either a 0 or a 1. A quantum computer uses qubits, which can be in a superposition of both. But the true power of a quantum computer comes from its ability to entangle these qubits. By entangling a large number of qubits, a quantum computer can create a vast, multidimensional computational space, allowing it to explore an astronomical number of possibilities simultaneously. This quantum parallelism is what gives a quantum computer the potential to solve certain problems, from designing new drugs and materials to breaking complex codes at a speed that is exponentially faster than any classical machine. The strange, non-local bond of entanglement is what allows the qubits to work together in a coherent, powerful harmony, unlocking a level of computational power that was previously unimaginable. But what if the significance of entanglement extends even beyond the realms of technology and into the very fabric of space-time itself? Some of the most exciting and speculative ideas in modern theoretical physics suggest that entanglement may not just be a phenomenon that happens in space-time, it may be the very thing that creates space-time. The ER equals EPR conjecture, proposed by the physicists Juan Maldacena and Leonard Susskind, is one of the most provocative of these ideas. It suggests a deep and surprising equivalence between two seemingly disparate concepts, quantum entanglement and wormholes. The conjecture posits that when two particles are quantum mechanically entangled, they are, in a sense, connected by a microscopic wormhole. This is a staggering idea. It suggests that the strange, non-local connection of entanglement is actually a manifestation of a deeper, geometrical connection in a higher dimensional space. It implies that the geometry of spacetime is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is woven from the intricate and complex web of quantum entanglements between the fundamental constituents of the universe. In this view, space is not the thing that separates us. It is the thing that connects us. A vast network of quantum threads, this idea, while still highly theoretical, provides a powerful and beautiful new lens through which to view the universe. It offers a potential path towards a theory of quantum gravity, a theory that can unify the two great pillars of modern physics. It suggests that the deep puzzles of quantum mechanics and the deep puzzles of general relativity may be two sides of the same informational coin, and it has profound philosophical implications. If the fabric of reality is woven from the threads of entanglement, then the universe is not a collection of separate, independent objects, but a single, holistic, and deeply interconnected whole. This is a worldview that resonates with the deepest intuitions of many spiritual and contemplative traditions. The idea that we are all one is not just a poetic sentiment. It may be a deep, physical truth, a truth that is written in the non-local, entangled language of the cosmos itself. The implications of this for our own human experience are vast and largely unexplored. If our own consciousness is, as some have speculated, a quantum phenomenon, then we too may be part of this universal entangled web. The feelings of empathy, of connection, of collective consciousness may not be just psychological phenomena, but may have a real, physical basis in the entangled nature of our own being. Imagine a future where entanglement is not just a topic for the laboratory, but a practical and integrated part of our everyday lives. Our most sensitive data is transmitted with perfect security through quantum encrypted networks. Quantum computers are solving some of humanity's most pressing problems, from climate change to disease, and perhaps even our understanding of ourselves, of our own interconnectedness, will have been transformed by this deep quantum insight, for all its promise. Entanglement reminds us that the universe retains its deep and beautiful mysteries. It challenges our most basic intuitions about causality, about distance, about reality itself. It urges us to rethink our place in a cosmos where the boundaries between here and there, between now and then, between self and other, may be far more fluid and far more mysterious than we ever imagined. What we have uncovered so far is merely the tip of a vast and magnificent iceberg. And with each new experiment, with each new theoretical insight, the strange and beautiful world of quantum entanglement continues to provoke, to puzzle, and to inspire. It is an invitation, not just to scientists, but to all of us, to look closer, to think deeper, and to imagine a universe that is far more interconnected and far more wonderful than it first appears. The universe is a sprawling and often bewildering enigma, a puzzle that has captivated the greatest minds of humanity for centuries. We have observed its patterns, we have dissected its laws, and we have spun beautiful, intricate theories about its origins and its destiny. But what if we were to told you that the very fabric of reality itself could be understood in a radically new and powerful way? What if the universe, in all its vastness and complexity, operates not like a grand clockwork machine, but like a colossal and unimaginably powerful quantum computer? This is a paradigm-shifting idea, one that is emerging from the frontiers of theoretical physics and computer science. It is a vision that reframes our understanding of reality, suggesting that at its most fundamental level, the cosmos may not be made of matter and energy, but of information, and that the laws of physics are not just a set of static rules, but are a form of ongoing, dynamic computation. This concept of a computational universe blurs the line between the observer and the observed, between the physical and the informational, in a way that is both deeply challenging and profoundly beautiful. At the heart of this new paradigm lies a radical reinterpretation of the laws of physics themselves. The equations and the constants that we have so carefully mapped, from the elegant mechanics of Newton to the curved spacetime of Einstein and the probabilistic waves of quantum mechanics, may be better understood not as a description of reality, but as the operating system for reality. They are the rules, the algorithms, that govern how the state of the universe is processed and evolved from one moment to the next. Quantum mechanics, in this picture, becomes the fundamental programming language of the cosmos. It is a language that is not deterministic, but probabilistic. It does not deal in absolute certainties, but in a rich and complex landscape of possibilities. The wave function of a quantum system is not just a mathematical tool, it is a complete, informational description of that system, a catalog of all its potential states. And the process of measurement, the infamous collapse of the wave function, is a computational step. A moment when the vast, superpositional potential is processed and a single, definite output is rendered into our classical reality. The ongoing mathematical dance of quantum mechanics is what gives the universe its structure, its texture, and its very existence. Look deeper into this computational cosmos, and you will find the principle of quantum superposition, the astounding ability of a particle to exist in multiple states simultaneously. If you have heard of Schrödinger's cat with its ghostly existence between life and death, you have already grasped the central paradox of this concept. But on a computational level, superposition is not a paradox. It is a resource. It is the basis for a massive and natural form of parallel processing. A classical computer must handle a computation one step at a time in a linear sequence. But a quantum system, by virtue of its ability to exist in a superposition of all possible states, can explore a vast number of computational paths all at once. This opens up a breathtaking possibility. What if the universe itself is performing a kind of continuous, massive parallel computation? What if every quantum event, every collapse of a wave function, is a moment of information processing, creating ripples of newly computed reality that propagate through the cosmos? This would suggest that the universe has an inherent and almost unimaginable computational efficiency, a power that is far beyond anything we could ever hope to achieve with our own man-made technologies. Central to this model of a computational universe is the role of measurement. As we have seen, a quantum system exists as a cloud of possibilities until an observation forces it to collapse into a single, definitive state. In the same way, a computation is not just a sequence of potential solutions. It must, at some point, result in a definite output. The observer in this picture is not just a passive element of reality. They are an active and perhaps even necessary participant. Every time we make a measurement, every time we interact with the world in a way that resolves a quantum uncertainty, we are, in a sense, contributing to the ongoing computation of the universe's state. We are not just reading the cosmic code, we are helping to write it. But what happens when errors arise in this incredible cosmic system? Just as our own computers are prone to glitches and bugs, the universe is not immune to the disruptive influence of quantum noise and decoherence. Decoherence is the process by which a quantum system, through its unavoidable interaction with its environment, loses its delicate, superpositional nature. It is the process by which the strange, ghostly qubits of the quantum realm are effectively converted into the familiar, solid bits of classical information. This could be seen as a form of error. But what if the universe has a built-in mechanism for quantum error correction? This is a concept that is at the very forefront of the development of real-world quantum computers. The idea of encoding quantum information in a redundant way, so that it can be protected from the effects of decoherence. Could it be that the universe itself employs a form of natural quantum error correction? Could the remarkable stability and consistency of our physical laws be a consequence of an inherent informational redundancy in the fabric of reality? A system that is constantly correcting errors as they arise and preserving the deep computational integrity of existence. The computational nature of the universe is also reflected in the strange, non-local structure of quantum causality. In our classical world, cause and effect follow a clear linear chain of events. But in the quantum realm, as we have seen with entanglement, the relationships between events can be far more subtle and interconnected. Entanglement creates a form of spooky, non-local connection between particles that defies our classical intuition about space and distance. If we translate this into a computational model of the universe, it suggests that the flow of information may not be a simple, linear process. It may follow the intricate, entangled pathways of the quantum world. The processing of reality is not a straight line, but a complex, interconnected web, a graph of relational information where the state of one part can instantly influence the state of another, no matter how far apart they are. This leads to an even more radical idea. What if spacetime itself is not a fundamental, pre-existing background, but is an emergent phenomenon, something that is born from the processing of quantum information? Some of the most advanced theories of quantum gravity, like the holographic principle, suggest that the three-dimensional space we experience may be a projection, a hologram that is encoded on a two-dimensional informational surface at the boundary of our universe. In this view, the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space, the flow of time, the force of gravity. All of these could be emergent properties of a deeper, underlying quantum computation. We can see hints of this computational logic even in the processes of the natural world. Quantum algorithms, like Shor's algorithm for factoring numbers or Grover's algorithm for searching a database, are specific, highly efficient solutions that are optimized for quantum systems. And intriguingly, some of these quantum computational strategies share deep structural parallels with natural processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field. It is as if nature itself has, over billions of years of evolution, discovered and implemented some of the most efficient quantum algorithms. This brings us to the most tantalizing and most speculative hypothesis of all. If the universe is indeed a quantum computer, could reality itself be an intricately coded simulation? The simulation hypothesis. The idea that our entire existence might be a program running on a vast cosmic computer is one that has long been a staple of science fiction, but it is now being seriously considered by some physicists and philosophers. If this were true, it would provide a natural explanation for some of the strange, built-in limits of our universe, like the speed of light or the Planck length. These would not be arbitrary constants, but would be the processing speed and the pixel size of the underlying computational reality. The view of the universe as a quantum computational system does not just reframe our understanding of the physical world. It opens up vast, new frontiers for exploration. It forces us to reconsider age-old philosophical questions in the new and powerful light of physics and computer science. If the universe is computing reality, then to understand that computation would be to understand the ultimate nature of existence, and perhaps it would grant us an unprecedented ability to interact with and to shape that reality, to move from being just a variable in the cosmic algorithm to becoming one of its programmers. This perspective does not reduce the awe and wonder of existence. It enhances it. It imagines a cosmos that is alive with a ceaseless and almost unimaginably complex process of calculation, a universe that is mathematically encoding and processing every atom, every star, every galaxy. And it is a reality in which you, the conscious observer, are a crucial and integral participant, not a passive recipient of information. but a node in the network, influencing the system and being influenced by it, connected through the invisible, entangled threads of quantum information to every other part of this incredible, unending equation. Imagine for a moment that this vast, three-dimensional universe, with all its depth, its substance, its seemingly solid reality, is not as it seems. What if everything we experience, the space that separates us, the time that flows around us, the very matter that makes up our bodies, is an elaborate and beautiful projection, a cosmic hologram? What if our entire, rich, three-dimensional world is, in fact, a higher dimensional mirage? Its information compressed and encoded onto a simpler, two-dimensional canvas at the very edge of our cosmos. This startling and deeply counterintuitive idea is at the heart of what physicists call the holographic principle, and it is a concept that challenges the very fabric of reality as we know it, suggesting a universe that is fundamentally informational, a universe where the distinction between the container and the contained, between the boundary and the bulk, is not as clear as we once thought. The origins of this revolutionary idea lie in one of the most unlikely and most mysterious corners of the cosmos, the study of black holes. For decades, black holes were seen as the ultimate information destroyers. Their immense gravity creates an event horizon, a one-way membrane from which nothing, not even light, can escape. Any information that falls into a black hole seems to be lost to the universe forever, a direct violation of the fundamental quantum mechanical principle that information can never be truly destroyed. In the 1970s, the physicist Jacob Bekenstein, and later Stephen Hawking, discovered something remarkable. They found that the entropy of a black hole, a measure of its information content, is not proportional to its three-dimensional volume, as one would expect, but is proportional to the two-dimensional area of its event horizon. It is as if all the information about the three-dimensional objects that have fallen into the black hole is somehow stored or encoded on its two-dimensional surface. This was the first hint of the holographic principle. It was a suggestion that the information content of a region of space is not as extensive as it seems, that it can be fully described by a theory that lives on its boundary. This idea was given a precise mathematical form in the 1990s by the physicist Juan Maldacena in what is now known as the AD-CFT correspondence. This is a profound and powerful duality, a kind of mathematical Rosetta Stone that shows a precise equivalence between two, seemingly very different, physical theories. On one side of the duality, we have a theory of gravity, like string theory, that lives in a curved, five-dimensional anti-de Sitter space. On the other side, we have a quantum field theory, a conformal field theory that has no gravity and lives on the flat, four-dimensional boundary of that space. The correspondence states that these two theories are completely equivalent. Every question you can ask in the five-dimensional gravitational theory has a corresponding and equally valid question in the four-dimensional quantum field theory on the boundary. This is a stunning and revolutionary idea. It suggests that gravity itself, which we have long considered to be one of the fundamental forces of nature, may not be fundamental at all. It may be an emergent phenomenon, a holographic projection of a deeper non-gravitational quantum reality that lives on a lower dimensional surface. The three-dimensional world of our experience, with all its gravitational complexity, could be a hologram generated by the quantum interactions of particles on a distant, two-dimensional screen. This holographic vision of the universe has profound implications for our understanding of space and time. If the geometry of space-time is an emergent holographic property, then it may not be a smooth, continuous fabric at its most fundamental level. It may be quantized, made up of discrete, indivisible units, like the pixels on a computer screen. The search for this holographic noise, the subtle quantum graininess of space-time, is an active, if highly challenging, area of experimental physics. High-energy experiments at particle accelerators and precise, astronomical observations of the cosmic microwave background are both searching for the faint, indirect clues that could reveal the pixelated nature of our reality. If the holographic principle holds true, it would also force us to rethink our most basic notions of causality and locality. In a holographic universe, the idea that events are determined by their local causes and effects may no longer be the fundamental story. The unfolding of events in our three-dimensional bulk would be dictated by the complex, non-local quantum correlations and entanglements of the information on the two-dimensional boundary. The universe would be, in a very real sense, a holistic and interconnected system, where the part is always a reflection of the whole. This perspective also offers a new and powerful way to think about the nature of gravity itself. The physicist Eric Verlinde, building on the holographic principle, has proposed that gravity is not a fundamental force, but is an entropic force. It is an emergent phenomenon that arises from the thermodynamic principles of information. In this view, gravity is a consequence of the universe's tendency to maximize its entropy, a statistical force that pulls things together because it is the most probable configuration of the underlying informational degrees of freedom. This is a beautiful and compelling idea, one that connects the geometry of spacetime directly to the laws of information and thermodynamics. And the mathematical architecture for exploring these holographic ideas is provided by the powerful framework of quantum field theory, and particularly conformal field theory. These theories describe how the information on a lower dimensional boundary can give rise to the rich and dynamic phenomena of a higher dimensional space. The study of these intricate mathematical mappings is one of the most exciting and productive areas of modern theoretical physics, and it is providing us with new and powerful insights into the deep, and as yet unsolved, challenge of quantum gravity. The holographic principle offers a compelling and beautiful starting point for unifying the two great, and seemingly incompatible, pillars of modern physics, general relativity and quantum mechanics. It suggests that they may be two different, dual descriptions of the same, underlying, informational reality. Beyond its revolutionary implications for physics, the idea of a holographic universe raises a host of deep and unsettling philosophical questions. If our familiar three-dimensional world is, in some sense, an illusion, a projection of a more fundamental, two-dimensional reality, then what does this say about the nature of existence itself? Are we, as conscious three-dimensional beings, just complex patterns in a cosmic hologram? What are the ultimate limits of our knowledge, if the reality we are trying to understand is not the fundamental one? These are questions that push the boundaries of science and steer us into the deep, and often murky, waters of metaphysics, of epistemology, and of existentialism. The holographic principle is a profound and humbling reminder of the potential limitations of our own evolved cognition. Our senses, our brain, have been shaped by the pressures of natural selection to be effective tools for surviving and reproducing in a three-dimensional macroscopic world. They are not necessarily designed to perceive the ultimate, fundamental nature of reality. The world we experience is a user interface, a simplified, and likely very partial, representation of a much deeper and far stranger underlying reality. But it is this very drive to question, to look beyond the surface, to strive for a deeper understanding, that is the hallmark of our species. The holographic principle also invites us to reconsider our picture of science itself. Science is not a process of uncovering a single, fixed, and absolute truth. It is an evolving narrative, a story that we refine and rewrite with every new discovery. The idea that even our most fundamental concepts, like space and time, could be emergent, and perhaps even illusory, is a powerful testament to the open-ended and self-correcting nature of the scientific process. It teaches us that we must be prepared to question everything, to hold our most cherished theories with a degree of humility, and to be open to the possibility that the next great revolution in our understanding will come from a place we least expect. As we gaze into the deep mysteries of the universe, from the swirling, information-scrambling event horizons of black holes to the subtle, quantum fabric of space-time itself, the holographic principle stands as a beacon of what science can achieve when it dares to challenge its own most fundamental conventions. It is more than just a theory. It is a testament to the boundless creativity and the relentless curiosity of the human mind. And as we continue to explore the implications of this strange and beautiful idea, we are not just decoding the secrets of the cosmos, we are also, in a very real sense, decoding ourselves and our own mysterious and holographic place within the grand and perhaps illusory cosmic drama. The reality we perceive, with its solid objects, its linear flow of time, and its clear causal relationships, is like a beautifully woven and seemingly complete tapestry. But what if, on closer inspection, we find that the threads are not as tightly knit as they appear? What if we discover gaps, tears, and strange, unexplored patterns in this fabric we call existence? The journey into the heart of modern physics is a journey into this very realization. It is the discovery that our classical, common-sense picture of the world is a powerful but ultimately limited approximation of a much deeper, stranger, and more mysterious reality. And it is a journey that leads us to one of the most enigmatic questions of all: can we ever fully and completely decode the true nature of reality? The first and most profound challenge to our classical worldview comes from the quantum realm. The concept of an objective reality, the idea that the world exists with definite properties, independent of our observation of it, seems, at first glance, to be an obvious and necessary starting point for any scientific inquiry. A tree in the forest is a tree, whether we are there to see it or not. But quantum mechanics, with its strange logic of superposition and measurement, complicates this simple picture. The observer effect demonstrates that the very act of measuring a quantum system can alter its state. An electron does not have a definite position until we measure it. Before the measurement, it exists as a wave of probability. Our observation forces this wave to collapse into a single, definite location. It is as though the universe only paints the picture of reality once we decide to look at the canvas. This raises a deep and unsettling question: how much of what we perceive as real is a property of the world itself, and how much is a product of our interaction with it, a reflection of the questions we ask and the measurements we make? This inherent fuzziness of the quantum world is quantified by Heisenberg's uncertainty principle. At the most fundamental level, it is impossible to simultaneously know certain pairs of properties of a particle, like its position and its momentum, with perfect accuracy. The more precisely we know one, the less we can know about the other. This is not a limitation of our instruments. It is an intrinsic, built-in feature of nature. It is as if reality itself has a fundamental blurriness at its core, a limit to its own definiteness. This suggests that our quest for a complete and perfectly precise knowledge of the universe may be, in principle, an impossible one. This fundamental limit on our knowledge is not just a feature of the physical world, it is also a feature of the abstract, mathematical world we use to describe it. In 1931, the logician Kurt Gödel, in one of the most stunning intellectual achievements of the 20th century, proved his incompleteness theorems. These theorems show that in any sufficiently complex and consistent mathematical system, there will always be true statements that cannot be proven. within the rules of that system. Mathematics, the very language of science, the tool we use to build our theories of reality, is itself fundamentally and forever incomplete. This has profound implications. If even the abstract logical framework we use to understand the universe has inherent, unprovable truths, how can we ever hope to build a final, complete theory of everything? Gödel's work suggests that our knowledge will always be a work in progress, a system that can be made more complete only by introducing new and themselves unprovable axioms. The quest for an absolute final foundation for our knowledge is a logical impossibility. This inherent incompleteness of our theoretical frameworks is reflected in the ongoing and often contentious debates about the interpretation of quantum mechanics itself, the Copenhagen interpretation, the many worlds interpretation, Bohmian mechanics. Each of these offers a different and seemingly incompatible picture of the underlying reality of the quantum world. Each is a different and partial attempt to make sense of the same strange set of experimental results. The fact that, after a century of debate, there is still no consensus on which, if any, of these interpretations is correct is a powerful testament to the deep, and perhaps irreducible, mystery that lies at the heart of our most fundamental theory. But the limits of our knowledge are not just found in the bizarre world of the quantum or the abstract realm of mathematics. We also encounter them when we try to bridge the gap between the simple and the complex, between the microscopic and the macroscopic. This is the problem of emergence. The philosophy of reductionism, which has been a powerful and successful guiding principle in science, is the idea that we can understand a complex system by breaking it down into its simpler, constituent parts. We can understand the properties of a gas by understanding the behavior of its individual molecules. We can understand the chemistry of a protein by understanding the properties of its atoms. But this approach has its limits. There are many complex systems, from the flocking of birds to the functioning of a city, from the intricate folding of a protein to the emergence of consciousness in a brain, where the behavior of the whole seems to be more than just the sum of its parts. These systems exhibit emergent properties, novel and unpredictable behaviors that arise from the complex, nonlinear interactions of their many components. You cannot understand the beauty and complexity of a flock of starlings by studying a single starling in a cage. You cannot understand the subjective experience of consciousness by studying a single neuron under a microscope. The bridge between the microscopic laws of physics and the macroscopic, emergent realities of our world remains one of the great unsolved frontiers of science. The challenge of understanding complexity is not just a conceptual one, it is also a computational one. The idea that we could, in principle, simulate the entire universe on a powerful enough computer and thus uncover all its secrets is a tempting one. But the theory of computational complexity suggests that this may be an impossible dream. There are many systems in nature that are computationally irreducible. This means that there is no shortcut, no simpler calculation that can predict their future behavior. The only way to know what they will do is to let them do it, to run the simulation, step by step, in real time. The weather is a classic example. Even with the most powerful supercomputers, we cannot predict the weather with perfect accuracy beyond a few days, because the system is so complex and sensitive to initial conditions that small errors in our model are rapidly amplified. The universe itself may be the ultimate, computationally irreducible system. If this is the case, then a complete, predictive knowledge of its future is not just practically, but fundamentally impossible. The universe's story can only be told by living it. This inherent unpredictability is not just a matter of complexity. It is also a matter of the fundamental, probabilistic nature of the quantum world. As we have seen, the universe, at its core, is not deterministic. It is governed by the laws of probability. We can never predict with certainty when a single radioactive atom will decay. We can only know the probability of it decaying in a given time interval. If the universe itself operates on this probabilistic logic, then how can we ever hope to map out a single, definite reality? We are not chasing a single, hidden answer. We are trying to understand a vast and constantly unfolding landscape of possibility. All of these limits the uncertainty of the quantum world, the incompleteness of mathematics, the emergence of complexity, the irreducibility of computation, the probabilistic nature of reality bring us to a final and deeply philosophical question. Are these barriers epistemic, meaning they are a result of our own human limitations of knowledge and perception, or are they ontic, meaning they are a fundamental built-in feature of reality itself? Some philosophers in the instrumentalist tradition would argue that they are epistemic. Science is just a tool for making predictions, and its inability to provide a complete, certain, and final picture of reality is not a failure, but a reflection of its proper limited scope. Others, in the realist tradition, would argue that they are ontic. Our scientific theories, in their very structure, are telling us something deep and true about the nature of reality, that it is, in its essence, incomplete, uncertain, and open-ended. The quest to decode reality, then, is not a quest to find a final, single answer. It is a journey into an ever-deepening mystery. It is a process that requires not just intellectual rigor, but also a profound sense of humility, of wonder, and of acceptance of our own, and perhaps the universe's own, fundamental limitations. The tapestry of reality is not a finished work of art to be admired from a distance. It is a living, breathing, and constantly evolving fabric, and we are not just its observers, but an integral part of its intricate and beautiful weave. The strange and beautiful world of quantum mechanics, with its principles of superposition, entanglement, and measurement, does not just challenge our understanding of the physical world. It also offers a new and profound lens through which to view the deepest mystery of all the nature of our own consciousness. The dialogue between quantum physics and the study of the mind has long been a fertile, if often speculative, ground for inquiry, a place where the most advanced theories of science meet the most ancient questions of philosophy. Could it be that the way we perceive, think, and experience the world is fundamentally tied to the bizarre and counterintuitive logic of the quantum realm? At the very heart of quantum mechanics lies the concept of measurement, the process by which the ghostly probabilistic world of quantum superposition collapses into the definite, singular reality of our classical experience. As we have seen, the role of the observer in this process is deeply enigmatic. While most physicists would argue that a conscious mind is not necessary for the collapse to occur, the very structure of the theory, with its inherent distinction between the unobserved system and the observing apparatus, seems to hint at a special role for information and awareness. This has led some thinkers to propose a more direct link between the quantum and the mental. Could our own subjective experience of a single, coherent reality be a macroscopic reflection of this fundamental process of wave function collapse? Could each moment of conscious awareness be a moment of quantum decision, a point where the vast superpositional potential of our brain's neural activity is resolved into a single, definite thought, feeling, or perception? This brings us to the fascinating idea of cognitive superposition. In our everyday waking lives, our minds often seem to entertain multiple and sometimes contradictory possibilities at once. In a moment of indecision, we can feel the pull of different choices. We can mentally simulate different potential futures. A classical computational model of the brain might see this as a simple, sequential process of weighing different options. But a quantum perspective offers a more radical possibility. Could the brain, at some level, be operating like a quantum computer, capable of holding these different possibilities in a genuine physical state of superposition? Could our subjective experience of indecision be the conscious correlate of an uncollapsed superpositional state in the quantum activity of our neurons? This is a bold and highly speculative idea, but it is one that is being taken seriously by some researchers at the frontiers of neuroscience and quantum biology. The search for a physical quantum basis for consciousness is not just a philosophical fancy. It is a field of active, if controversial, scientific research. We know that biological systems are not just classical, chemical machines. There is growing evidence that certain biological processes, from the way that plants perform photosynthesis to the way that birds navigate using the Earth's magnetic field, may be harnessing the strange and powerful effects of the quantum world. Could the human brain be another example of this quantum biology? The orchestrated objective reduction theory, proposed by the physicist Sir Roger Penrose and the anesthesiologist Stuart Hameroff, is the most well-known and specific model for how this might work. It posits that the fundamental units of quantum computation in the brain are not the neurons themselves, but the microtubules, the tiny cylindrical protein structures that form the cytoskeleton of our cells. Penrose and Hameroff argue that the quantum states within these microtubules can exist in a superposition of different configurations, and that these superpositions are the physical basis of our pre-conscious processing. Consciousness in this model arises at the moment of objective reduction, a spontaneous collapse of this quantum superposition that is triggered by a fundamental gravitational instability at the Planck scale. Each of these collapse events, happening many times a second, corresponds to a single, discrete moment of conscious experience. The OR theory is highly speculative and faces a number of significant scientific challenges, particularly the question of how a fragile quantum state could be maintained in the warm, wet, and noisy environment of the brain. But it is a testament to the growing interest in exploring the potential quantum nature of the mind. The observer effect in quantum mechanics, the idea that the act of observation can influence the state of a physical system, also finds a powerful metaphorical, and perhaps even literal, resonance in our understanding of consciousness. Our attention, our awareness, is not a passive spotlight that simply illuminates a pre-existing mental landscape. It is an active, creative force that shapes and transforms our inner world. When we bring a quality of mindful, non-judgmental awareness to a difficult emotion, like fear or anger, we can often feel its energetic quality shift and change. The act of observing it, without being identified with it, seems to collapse its power, to transform it from a solid, overwhelming reality into a more fluid and manageable experience. This is the basis of many contemplative and therapeutic practices. And it is an experience that hints at the possibility that our consciousness is not just a product of the brain, but is a fundamental, causal agent in the brain, a force that can influence the very physical processes that give rise to it. The bridge between the quantum and the classical, the strange and the familiar, may be found in the process of decoherence. As we have seen, decoherence is what explains why we do not experience the world as a constant, blurry superposition. A quantum system, through its unavoidable entanglement with its environment, rapidly loses its quantum coherence. The information about its superposition is spread out into the surrounding world, and for all practical purposes, the system behaves classically. This principle is what safeguards our classical, everyday reality from the bizarre, underlying quantum weirdness. But it also offers a new way to think about the nature of perception itself. Our sensory organs, our eyes, our ears, our skin are macroscopic measuring devices. They are constantly interacting with and entangling with the quantum systems of the external world. The act of perception is a process of decoherence. When a photon from a distant star hits a retinal molecule in your eye, it triggers a cascade of classical chemical events. The quantum information of the photon's superpositional state is effectively measured and collapsed into a definite classical signal that is then processed by your brain. Our classical perception of the world is, in this sense, a consequence of the constant entropic loss of quantum information. We see a definite, classical world because our very act of seeing is a process that destroys the underlying quantum reality. This leads to a profound and humbling conclusion. The reality we experience is not the full reality. It is a collapsed reality, a simplified and likely very partial representation of a much richer and far stranger quantum world. The discussion of consciousness and quantum mechanics inevitably leads to the age-old debate about free will. A classical deterministic universe, governed by the clockwork laws of Newton, seems to leave no room for genuine freedom. Our choices would be nothing more than the inevitable outcome of a long chain of prior causes and effects. But the quantum world, with its inherent irreducible randomness, seems to open a door. The collapse of the wave function is a probabilistic event. The outcome is not predetermined. Some have argued that this quantum indeterminacy could be the physical basis for our experience of free will. Perhaps our choices are not the result of a deterministic, computational process in our brains, but are, at some level, the result of the amplification of these random quantum events. This is a controversial idea, as it seems to equate free will with pure chance, which is not what we usually mean by freedom. But a more sophisticated version of this idea suggests that our conscious mind may be able to influence the probabilities of these quantum events, to steer the collapse of the wave function in a way that is consistent with our intentions, without violating the statistical laws of quantum mechanics. This is a deep and difficult problem, and one that is far from being solved. But the dialogue between quantum mechanics and consciousness, for all its speculative nature, is a powerful and important one. It is a dialogue that is pushing the boundaries of both science and philosophy. It is forcing us to question our most basic assumptions about the nature of reality, of the mind, and of the relationship between the two. It is a reminder that the universe is far more intricate, far more interconnected, and far more wondrous than our classical intuition can ever reveal. And it is an invitation to explore the deep and as yet uncharted territory where the mysteries of the outer cosmos meet the mysteries of our own inner world. The universe is brimming with information. It is encoded in the complex, swirling patterns of a galaxy, in the precise, orbital dance of a planetary system, in the fiery thermonuclear heart of a star, in the elegant double helix structure of a DNA molecule, and in the strange probabilistic wave function of a single subatomic particle. From the grandest cosmic scales to the most infinitesimal quantum ones, information is the thread that weaves the fabric of reality. But what happens to this information over the long and often violent course of cosmic history? Is it preserved forever, a perfect, indelible record of all that has ever been? Or can it be lost, erased, destroyed in the great entropic wash of time? This is one of the most fundamental and deeply debated questions in all of modern physics. A question that touches on the nature of time, of entropy, of black holes, and of the very laws of the universe itself. To understand the fate of information, we must first understand its foundations in both classical and quantum physics. In the classical world, information is, in principle, always preserved. This is a direct consequence of the deterministic nature of classical laws. If you know the precise state of a closed system at one moment in time, the position and velocity of every particle, then the laws of physics allow you to, in principle, calculate its state at any other time, both in the future and in the past, Information is never lost. It is just rearranged. But the quantum world, as we have seen, operates on a different logic. The process of decoherence seems to imply a fundamental loss of information. When a quantum system interacts with its environment, the information about its delicate superpositional state is rapidly spread out and dissipated, becoming, for all practical purposes, irretrievably lost. This is why our macroscopic world appears to be classical, even though it is built from quantum components. The quantum weirdness is constantly being washed away by the entropic tide of environmental interaction. Understanding and controlling this process of decoherence is one of the central challenges in the development of practical quantum technologies. To build a powerful quantum computer, we must find ways to isolate our qubits from their environment, to shield them from the relentless process of decoherence, long enough for them to perform their complex calculations. The quest to build a quantum computer is, in a very real sense, a battle against the informational entropy of the universe. The deep and intimate connection between information and entropy is a cornerstone of modern physics, a connection that is most beautifully illustrated by the laws of thermodynamics. The second law of thermodynamics, as we have seen, states that the entropy, or disorder, of a closed system always increases over time. This is the law that gives time its arrow. But information can be seen as the very opposite of entropy. It is a measure of order, of structure, of reduced uncertainty. When we gain information about a system, we are, in a sense, locally reducing its entropy. This is the paradox of Maxwell's demon, the hypothetical being who could seemingly violate the second law by sorting hot and cold molecules. The resolution to the paradox lies in the realization that the demon itself, in the process of acquiring and processing information, must generate at least as much entropy as it reduces, thus preserving the overall validity of the second law. This connection was made even more explicit by Landauer's principle, which states that the erasure of information is an irreversible, entropy-increasing process. To erase a single bit of information from a computer's memory, you must release a minimum amount of heat into the environment. Information is not an abstract, disembodied entity. It has a real physical cost. It is tied, by the fundamental laws of nature, to the world of energy and entropy. On the grand cosmic scale, the universe itself can be seen as a vast and ancient repository of information. The cosmic microwave background, the faint afterglow of the Big Bang, is not just a uniform glow. Its tiny temperature fluctuations are a snapshot of the primordial information, the quantum seeds from which all the structure in the universe grew, the large-scale distribution of galaxies, the intricate chemical composition of the stars, the complex geological history of a planet. All of these are records. Archives of the universe's long and complex evolutionary story. But what is the ultimate fate of all this cosmic information? Does the universe have a finite memory? The accelerating expansion of the cosmos, driven by dark energy, raises a profound and unsettling possibility. If the universe continues to expand at an ever-increasing rate, then the information contained in distant galaxies will eventually be stretched and redshifted into oblivion, lost forever beyond our cosmic event horizon. The observable universe will become an increasingly barren and information-poor place. And the enigmas of dark matter and dark energy add another layer of mystery. Does dark matter, which makes up the vast majority of the matter in the universe, play a role in storing or processing information? Or is it an informationally inert, passive background? And what is the informational nature of dark energy itself? Is it a simple, constant energy of the vacuum, or is it a dynamic, information-rich field that is evolving over time? These are some of the most profound and challenging questions in all of cosmology. Perhaps the most intriguing and challenging intersection between information and the cosmos lies in the nature of gravity itself. For decades, the quest to unify general relativity and quantum mechanics has been the holy grail of theoretical physics, and in recent years, a new and powerful idea has emerged that gravity itself may not be a fundamental force, but an emergent phenomenon, something that arises from the deeper quantum informational structure of the universe. The idea is that the very fabric of space-time is woven from the threads of quantum entanglement, the geometry of space. The curvature that we perceive as gravity is a macroscopic manifestation of the intricate web of quantum correlations between the fundamental constituents of reality. In this view, information is not just in the universe is information. This is a radical and beautiful vision, and it is one that is supported by the holographic principle. The idea that all the information in a three-dimensional volume can be encoded on its two-dimensional boundary. This principle, which first arose from the study of the thermodynamics of black holes, suggests that our familiar three-dimensional world may be a kind of cosmic hologram, a projection of a more fundamental, two-dimensional informational reality. This would have profound implications for the black hole information paradox. If the information about the matter that falls into a black hole is encoded on its two-dimensional event horizon, then it is never truly lost to the universe. As the black hole evaporates, this information could be subtly and complexly imprinted onto the outgoing Hawking radiation, thus preserving the fundamental principles of quantum mechanics. And what of the ultimate fate of the universe in this informational picture? If the universe is destined for a heat death, a state of maximum entropy where all energy is evenly distributed and no useful work can be done, would this also be a state of information death? Would all the complex ordered information that has been created over billions of years of cosmic and biological evolution be lost in a final, uniform sea of thermal noise, or could information persist? Even in this seemingly final state, some speculative theories suggest that even in a heat death scenario, the quantum fluctuations of the vacuum would continue, and that over immense, almost unimaginable timescales, new ordered structures could spontaneously fluctuate into existence. The universe could, in a sense, be reborn from its own informational ashes. The study of information in physics is a rapidly evolving and incredibly exciting field. It is a field that is blurring the lines between physics, computer science, and philosophy. It is forcing us to rethink our most basic concepts of reality, of space, of time, of causality. And it is a field that is driven by a single, powerful, and unifying idea that to understand the universe, we must understand its information. The cosmos is not just a collection of matter and energy. It is a story, a message, a vast and ongoing computation. And in learning to read this cosmic code, we are not just deciphering the secrets of the universe. We are also, in a very real sense, discovering the deep informational nature of ourselves. The future of humanity has always been inextricably linked to our ability to create, to process, and to transmit information. From the invention of language and writing to the development of the printing press and the internet, every major leap in our information technology has been a major leap in our civilization. And today, we stand on the cusp of a new and potentially even more transformative revolution. A revolution that is being driven by the strange and powerful logic of the quantum world. The future of information is a story of two converging technologies, artificial intelligence and the quantum internet. And their combination holds the promise to redefine not just our technology, but the very fabric of human existence. Artificial intelligence, once the stuff of science fiction, is now a ubiquitous part of our everyday lives. It is in the virtual assistants that organize our schedules, in the recommendation algorithms that shape our cultural tastes, in the sophisticated systems that help doctors to diagnose disease and scientists to analyze vast and complex data sets. The power of modern AI lies in its ability to learn from data, to recognize patterns, and to make predictions with a speed and an accuracy that can far surpass human capabilities. But for all its power, our current AI is still limited. It is a form of narrow AI, a system that is incredibly good at performing specific, well-defined tasks, but that lacks the general, flexible, and creative intelligence of a human mind. The story of AI is still in its early chapters, and the next, and perhaps most exciting, chapter may be written in the language of quantum information. The concept of quantum information, as we have seen, is a radical departure from the classical binary logic of our current computers. A quantum computer, by harnessing the principles of superposition and entanglement, can process information in a fundamentally new and more powerful way. It can explore a vast, multidimensional computational space simultaneously, giving it the potential to solve certain classes of problems that are, for all practical purposes, unsolvable for any classical machine. Imagine an AI system that is not limited by the linear, step-by-step logic of a classical computer, but can think in the rich, probabilistic, and superpositional language of the quantum world. This is the promise of quantum AI. Why? A quantum AI could, in principle, analyze a vast and complex landscape of possibilities in an instant, allowing it to solve complex optimization problems, to design new materials with novel properties, or to discover new drugs by simulating the quantum behavior of molecules with perfect fidelity. It could be an engine of scientific discovery and technological innovation of unprecedented power. But the quantum revolution is not just about computation, it is also about communication. And this is where the second part of our story begins, the development of the quantum internet. A classical internet transmits information as bits of data encoded in pulses of light or electrical signals. A quantum internet would transmit information as qubits encoded in the quantum states of single particles, like photons, and its primary, and most revolutionary, feature would be its inherent and perfect security. As we have seen, the principles of quantum mechanics, like the no-cloning theorem and the observer effect, make it impossible to intercept or copy a quantum communication without being detected. A quantum internet would be a truly unhackable network, a development that could revolutionize every industry that relies on the secure transmission of data, from finance and government to healthcare and defense. But the potential of a quantum internet extends far beyond secure communication. It would also be a network that can transmit entanglement. It would allow us to create and distribute these strange, non-local quantum connections between distant quantum computers, linking them together into a single, global quantum computational network. This would allow us to tackle problems that are too large and complex for even a single, powerful quantum computer. It would be a new kind of global collaboration, a new way of harnessing the collective, computational power of the quantum world. Now, let us think even bigger, even more speculatively. What is the ultimate, long-term potential of this quantum information revolution? The astrophysicist Nikolai Kardashev famously proposed a scale for categorizing hypothetical and advanced extraterrestrial civilizations based on their ability to harness energy. A Type 1 civilization is one that can harness all the energy of its home planet. A Type 2 can harness all the energy of its host star, and a Type 3 can command the power of its entire galaxy. We can imagine a similar scale for the mastery of information. What if a future advanced civilization could learn to harness and process information on a cosmic scale? What if they could build a galactic-scale quantum internet, A network that connects not just computers, but planets, stars, and perhaps even different regions of space-time. This is a provocative and highly speculative notion, but it is a logical, long-term extension of the technological trajectory we are on. If information is the currency of intelligence, then the ability to manage information on a cosmic scale could allow a civilization to unlock secrets of the universe that we can't even begin to comprehend. Could this be an evolutionary milestone for advanced life? Could the mastery of quantum information be the key to reaching a new and higher level of cosmic consciousness? Naturally, these bold and futuristic ideas spark a host of profound ethical and philosophical questions. The development of a true general artificial intelligence, whether classical or quantum, would be a watershed moment in the history of life on Earth. How would we ensure that such an intelligence is aligned with human values? How would we prevent it from being misused? What would be our own role and purpose in a world where we are no longer the most intelligent beings on the planet? These are not just technical challenges, they are deep, societal, and existential ones. Similarly, the development of a global quantum internet, while offering the promise of perfect security, also raises questions about privacy, surveillance, and control. Who would own and control this new fundamental layer of our information infrastructure? How would we ensure that its benefits are distributed equitably and that it does not become a tool for creating an even wider gap between the haves and the have-nots of the information age? The democratization of these powerful new technologies will be one of the most critical challenges of the coming century. And of course, there are the skeptics. Some argue that the warm, wet, and noisy environment of a biological brain is simply not conducive to the kind of delicate, coherent quantum processes that would be needed for a quantum mind. Others argue that even a powerful quantum AI would never be able to replicate the true, subjective experience of human consciousness, with all its intuition, its creativity, its capacity for love and sorrow. These are valid and important critiques, and the debate is far from settled. But even if the most ambitious claims for quantum consciousness and AGI do not come to pass, the journey itself is transforming our world. The promise of quantum information is reshaping our understanding of artificial intelligence. The development of the quantum internet is redefining the future of communication. And the futuristic vision of a civilization that can harness information on a cosmic scale is providing a new and powerful lens through which to view our own long-term evolutionary future. The future of information is not just about faster computers or more secure networks. It is about redefining what it means to live in an interconnected, intelligent, and information-rich world. It is about uncovering new truths, not just about the universe, but about ourselves. It is about understanding what a civilization can achieve when its technological innovation is guided by its deepest imaginative and ethical aspirations. As we conclude this exploration, the question we are left with is not, what is the future of information? But rather, how will we choose to shape our future with the new and powerful forms of information that we are now, for the first time in history, beginning to create? The possibilities are infinite, the questions are profound, and the answers, for now, are waiting for us in the strange, beautiful, and endlessly creative quantum unknown.